in the chemical engineering and material science, and it will be my pleasure to introduce the speakers in the afternoon session. Just to clarify, there were some questions about it. Apparently, technically, we have 25 plus 10 minutes as the format, but 30 plus 5 works just as good. So I will wait at 25 just to let you know. All right. Okay. So the first speaker of our afternoon session is Peter Littlewood, and he will be talking about the modulated phases in the so-called quantum ferroelectric Strontium Titanate.
Yeah, thank you very much. So I think I'm the first one who's talking about Strontium Titanate. There are a lot of experts in doing this, but I will, for those of you who are not experts, I'll begin actually by just saying something about the basic phenomenology. What I do want to say before I start is the people who did the actual work, and I've learned over time to put this up as my first slide and not my last slide. Because, so that's to say that there's really several distinct pieces of work on here. Work actually on the structure of the oxides was done by two graduate students, Alex and Charles, and a former postdoc who's now professor at Costa Rica. Some work that I probably won't get to, which was on Ferroelectric bipolaron, was done by these three people. Lisa, starting this actually when she was an undergraduate in Chicago, and she's now a grad student at MIT. And Julian was a postdoc at Flatiron. Shiwei was a staff scientist. And I will also show some data from various experimental collaborators, particularly from Peter Abramonte's group, from Pelc, from group in Cambridge, Nano-Lens Richmond, Sarah Shiwei, and also now Matt Koch is going to be running it, and some recent data from SNAC. So, what's the outline of the talk? So, the main thing I will talk about, I suspect, is that strontium titanate is a material which is very close to being ferroelectric, but doesn't quite make it. That's been a famous problem ever since the 70s, and it's provoked all kinds of thinking. And sometimes, when it is a quantum critical point, by definition, it's close to that. But the question really is why, and I'm not sure I have an answer to that necessarily from phenomenology. Possibly related, but not necessarily related. There's another reason it's strontium titanate that is interesting. Is it's actually a superconductor. It's a superconductor at extremely low Kelvin distance. However, it's a high TC superconductor, even though TC never gets to 1 Kelvin. You're in a regime where the Fermi temperature is 10 Kelvin. And all of the relevant modes that it is coupling to are bigger than the Fermi temperature. So why it is doing that is also provoked a lot of interest. And I'm going to make some comments. I don't think I have a theory. I've had theories, but they were all wrong. I may tell you about some wrong ones. And there is very strong coupling to longitudinal optic phonons, so-called Ferroelectric. It's extremely strong. And that makes you think possibly about so-called Ferroelectric bipolarons. And if I have time, I'll try and get to them, but I'm not sure. But this is sort of an advert that I'll be around in weeks. I'm very happy to talk about it. A little bit of background. Strontium titanate is a three-dimensional perovskite. So it's basically cubic, white. It has the titanium sitting in the middle of an oxygen octahedron, and strontium at the edges of the cube. And it has some instabilities. As you cool it down at high temperatures, it actually is cubic. When you get to 105 Kelvin, it goes in a small deformation from cubic to tetragonal. I'm in general going to ignore that. And the one which is of interest actually is that the titanium atom has a tendency to go off center. How do you know that? You know that because, of course, if it does go off center, it will generate a dipole moment, and the material will become ferroelectric. And the proximity to ferroelectricity, of course, involves looking at the dielectric constant, the antipode, the inverse of the dielectric constant. And so this is rising. This is actually basically Curie law. And the Curie law heads for what you would have thought to be a phase transition of about 30 Kelvin or so. But then when it gets in the vicinity of that, it saturates that. but it flattens out at an enormous number. So this is 10 to the minus 3 times the dielectric. So the dielectric constant is an order 20,000. So it's right on the brink of being ferroelectric at T equals 0. And the question for a long time is, what is this? A little bit more look at that phase diagram, and this is data from the Cambridge group, which is actually under pressure. So this is temperature pressure plot. And here, if you like, you're looking at the dielectric susceptibility, and at ambient pressure, you see that this diverges, or almost diverges. However, if you put the system under pressure, you move away from the quantum critical point of this saturate. But if you look closely in the vicinity of there, there's a whole bunch of crossovers. I think some of them Premium may talk about later today, because we're fairly sure what the physical origin of these is. But the odd thing about them is that there are several. More than one might have expected. You can actually go along the other axis. You do that by going to oxygen 18. And oxygen 18 does actually form a state. You can also make the system ferroelectric by doping with the right kinds of things. And you see that too. But there's a sort of generic phase diagram. I am going, yes.
How do you know that the going to oxygen 18 is like negative pressure and not just increasing the mass of the oxygen?
Because actually there's a negative isotope. Well, so the answer is you know. I didn't put that part, but that's that if you like is the there is a if you do that scaling just with the lattice constant.
Yeah, works. Nice.
And by the way, there's a whole bunch of other things that one can do. You can apply anisotropic stress, and sometimes you go to the right, and sometimes you go to the left. And so there's a whole sort of zoology of all of these things. So to a great extent, there are other ways of parameterizing that line.
But just the amplitude of oxygen oscillation will get smaller.
Yeah.
So it's like effectively making it smaller.
That is the story of that. Right. And there's another oddity associated with oxygen. So actually, what I want to talk about, for the purposes of this talk, is coupling to elastic strain. And there are two natural forms of that. Is that if I've got an order parameter, there's a vector of polarization peak, and in a material which is cubic, and it isn't quite cubic, but I'll pretend it is, you would have a coupling which will be the elastic strain will couple with the square of the polarization. So non-linear term. That's called electrostriction, and that does interesting things, which I'm not going to talk about. I want to focus actually on something else, which is generically called flexoelectricity, which is a harmonic coupling. And so this is a coupling linearly of the order parameter to the strain, but it's a coupling to the gradient. So that means that in terms of modes at q equals 0, there is no coupling, but this turns out q. And I'd like to ask what this might do. And I'm going to give you that kind of story, in a simple phenomenology. And then we'll come back to some of the other things associated. So at the moment, I'm just going to talk about this phenomenon and what it might have to do with extraction.
Is there a similar term that couples the gradient of the strain to the polarization?
Yeah,
It's identical.
you could just, I mean, you can write it in a symmetric form if you like. If I write that in a Hamiltonian, epsilon grad P, I can obviously turn into P grad epsilon minus some boundary steps. So both terms must exist. This is just to show you how solves the equations. So read the equations. I'm going to do the simplest self-consistent field theory that one can do, or if you like, applied Hall theory for the polarization. So some optic mode which is softening, so it's stabilizing nonlinearity, coupling to acoustic fields. But to understand what might happen, I just put in some approximate parameters for something like actually potassium tank. if you have your Baire theory without this couplings, you will have some, so this is omega versus Q. So this is the TO-phonon, just coming down and getting very soft. And that's the TO-phonon whose vanishing produces the divergence effect of the dielectric action. But one should also remember that there's an acoustic. There's no coupling between these modes at Q equals 0, but the coupling turns on at finite Q. And so what you can see, of course, is that if this mode comes, as you cool the temperature comes down and gets soft, it's going to push on that acoustic. If that coupling is big enough, you can drive the acoustic modes. And I'd like to take that as a hypothesis and come back to see if that works. Now, this isn't a new idea. This is, if you look at many classes of ferroelectrics, quartz is one. You can go from the normal phase into a ferroelectric phase via an intermediate phase, which is incremental. It's in fact very common that there are phases which have, if you look, very long period order on the edge of ferroelectricity. It's kind of a standard thing. It's actually quite well known because this coupling can in fact be big. So let's ask, in fact, what might happen as a function of the phase diagram. And here I'll sort of talk you through the algebra. So let me first start. What I'm going to do is, I'm going to give you, firstly, the boneheaded mean field theory with two parameters in. One is temperature along this axis, another is, if you like, the flexoelectric coupling, the magnitude of that. So it starts with 0, there's some critical coupling. And that critical coupling at the mean field level is just associated with when you come down here, so now we're looking at the TO mode frequency. If the critical coupling was too small, all that happens is the TO mode frequency goes through 0. I get this line. And then actually, if it's big enough, what happens is that the TO mode frequency doesn't go soft anymore, but instead I go soft, so modulated phase. And I would get a stripe song. That's all there is at the level of Landau theory. Now, let me put in the leading order quantum fluctuations.
Peter,
Yeah.
before you put in quantum fluctuations, what sets the Q vector?
So the Q vector varies continuously from this.
Okay,
It starts at 0, and then it moves out.
okay, thank you.
So the stripe period is so now let me actually put in not quantum fluctuations, but classical fluctuations. So here the point is again relatively trivial. Suppose I'm in a situation where this mode goes soft at some finite Q. The theory I gave you, and actually in practice, because I'm at such very long wavelength, the system is going to look isomorphic. So what I know from this is that I'm supposed to get some modulation wave vector at some amplitude Q, but I don't know the direction it's going. So that's a vector which has to find its way on the surface of a sphere in a three-dimensional system. And actually, in a d-dimensional system, it has a d-1 dimensional space to fluctuate in. And that means you add any thermal fluctuations to that, and it will destroy the order, and it'll become a nematic lamella. So sort of established soft metal physics. So then what happens is that you would get, so you begin to suppress the ferroelectricity, it vanishes here, and then here you go into something which in principle would be a liquid. But as you lower the temperature, thermal fluctuations go like T. The correlation length will get longer and longer. And in principle, then, at low temperatures, you will get a modulated stripes.
So is that clear? You're assuming that at low temperatures you will get single Q. So
Well, yeah, but you think it would still be a striped solid. It doesn't know which Q, but there's no fluctuation.
but why not a combination of more than one Q at low temperatures?
Well, okay, but I can do that with quantum mechanics. Right. So then, if I turn on quantum mechanics, this long range, so the correlation length will grow and grow and grow and grow. Right? But eventually, I'll start spinning around in this well just because of quantum fluctuations. It's just 0 point. It's not tunneling or anything like that. I've just got 0 point occupancy of all of these modes. And that 0 point occupancy would be enough, actually, to prevent the establishment of non-majority.
It's clear that there are no higher order terms that picks a certain crystallographic direction. for the
Absolutely,
modulation.
so there are. So obviously, for example, the electrostrictive terms will generate nonlinear terms which will know about asymmetry. You know, and there's a whole zoo that one might play around with here, for example, of thinking about, you know, phenomena like order from disorder, because basically the higher order terms would be visible at finite temperature because you begin to explore those and then the system decides where it's going to go. So I think in anything realistic down here, it's either going to freeze or order or whatever. And indeed, so I'm just sort of neglecting all of this stuff because I want to give you a story. And this only makes sense if it has anything to do with experiment. And then if it does have, it might have something to do with experiment, which kind of enhance the story and chase it down. So I'm not saying that quantum fluctuations aren't important. There still is a quantum critical point sitting here, but it's a very different physical story than one had going back to Muller, because Muller talked about this as quantum fluctuations having destabilized the ferroelectric fields. And that was always a little scary because if you imagine it's sort of a double well potential, by the time the dielectric constant has got to 20,000, the coherence length for the fluctuations is a couple of nanometers. And so if you want to think about quantum fluctuations in a double well potential, you have to imagine several thousand atoms spontaneously tunneling from one side to the other. And that didn't, this is a bit easier because all I'm using is 0 point and a very good alphas. Okay. Is there any evidence? And I'm using it, we're doing all of this, and then we got scooped by this paper. This paper by okay. And this is neutron scattering data. And let me talk you through this figure here. So what you're looking at here is from high temperature up here, the yellow curves, to low temperature, which is the darker blue. The measurement is being done just off of Bragg peak, 0.05, 0.05. So this is inelastic scattering energy in this direction. But you're sitting at a Q vector, which is a little bit off the Bragg peak. And so for that reason, you can actually see the acoustic mode as well as the optic. And so the thing you notice here is that the optic mode is softening, as we expected. That's the divergent dielectric. But then if you look carefully, you can see that it's actually pushing the acoustic. And somewhere down at the bottom, you can't see the acoustic.
Oh, Peter, I was under the impression that what they were seeing was dynamical, whereas.
This is that.
Right, but what you're discussing is more static.
Absolutely.
Okay, I just wanted to double check.
So basically, we're looking at the mode structure of something about something else. We don't know what the underlying
Okay,
structure is.
I just wanted to make sure.
No, thanks, but no, this, if you like, is, from my perspective, might well be a precursor to something which is going to happen.
Very, thank you.
Right, so then if you look at that, then what you can really do is you can pick a couple of temperatures, which they did here, and also a bunch of different Q vectors. And to look at the change in the acoustic phonon frequency from one temperature to another. Now, because everything is pretty ratty down at low temperatures, they're really not going, they're showing only down to 20 Kelvin because that's the last time connections. So what you see is that for a Q vector somewhere around 0.02, there's a softening by about 50%, which is really actually quite a lot. Notice, of course, that this is still a solid. So if you measure the sound velocity at much longer wavelengths, which you can do, it really is not softening at all. It's just something that's happening, and also at larger wavelengths too. So this is something with a these are waves with a very long period. I don't have any evidence in this data, however, that any symmetry got broken, that there's an underlying phase which has all of those fluctuations.
I see Alaska name there. So
Sorry?
did he, I see Alaska Subedi there. So he's very good. Did he calculate this spectrum and found the softening as well?
Well, he's an author on this paper.
Yeah. So I wonder what he did there. Did he do calculations for
I
that?
don't know, actually. That's not something
He's
I
very
mean,
reliable.
actually, there's an interesting story associated with that issue. People who, strontium titanate is a non-correlated material. It's something where ab initio methods in principle work very well. So if you go and ask, ab initio calculators to calculate the structure of strontium titanate, they in principle can do it, but they have found it very hard. There are even some papers which got answers which basically say that the system is disordered even at T0. I don't quite know what happened to the third law of thermodynamics with that. But it turns out to be very, very difficult to stabilize these phases in those calculations. And the reason is that presumably that if something is producing a very long period of stability, you need a very large supercell to capture. Well, maybe you know better, but I say that no, but I mean, but
There are problems, but they're for different reasons. Anyway, we can talk about that.
well,
later.
okay,
I know
would
this.
be good to talk. So the answer is if you put strontium titanate in a standard supercell, standard cell calculation and try and minimize, right? There is no minimum.
Oh, yes, there is.
Right,
No,
because
the problem is that there are several which are
there are
very
several
close
which are
together.
right.
So this is which related to how this octahedra rotate. But it's a separate issue.
That's
He can do good phone calculation, this guy, I know.
Yeah, no,
I just wonder what he gets.
If you're going to do a Phonon calculation, you have to start with a stable structure. If you don't have a stable structure, there's no way to do the Phonon.
Even if the structure is stable though, in order to capture something at such a small wave
It would be
vector,
very-
you need a large
you need a very-
supercell or you need
No, no.
DFPT.
So
Yeah, that's what I do, DFPT.
Oh, yeah.
Yeah,
So-
and
so
he does very well.
Like the,
I mean, I agree. I think it's doable.
let's talk about, you need DFPT, that's specific wave vector, which is.
There's other data which actually shows some effects, but is not quite the same as that. So this is from Slack, a recent paper, and again, this is a much more complicated experiment because we're doing everything in the time domain. And this is, I would say, quasi-linear measurements. So again, what you can see is that this is a probe which is only sensitive to things with dipoles. So the TO mode you can't see that long wavelength because it doesn't have a dipole.
Sorry, maybe I have interrupted exactly. Since I know you're not in that paper, but do you understand why they don't see that, why the TA mode is way sharper than the TO mode? When they're sensitive to the dipole interaction, so they expect that you should see a little bit of the TA, but a lot of the TO, not the other way around.
I don't know.
Okay,
And as I say, this does not completely match.
okay,
Right, with this has much more oscillator strength. than this.
right.
And I think it's probably buried actually in details of this experiment, which is not simple.
Like a form factor.
There are all kinds of form factors which are in this. This shows some softening, but actually not much. And as you see, you're seeing here a much sharper one. So I don't really. But there's definitely evidence from a couple of this. But I do want to point out that this then begins to play a little bit into providing stories, again, just stories, for why one might actually have this sort of complicated series of concepts. I should say something about this. Oh, I'm going to talk about a few things. So, I don't actually really know what's going on here. I think that there's quite a lot of complexity, and there's some more that will show you. But it would be interesting if there was some kind of radical situation. So remember, without electrons. And then, of course, you might ask what happens when I add electrons. I'll show you some of that. Superconductivity. So let me just give you some background. No, so this, if you like, is TC versus doping. There's been a lot of work done on this going a long way back, and it's not. We're dealing with very small carrier densities of very substantial TCs. But there's a dome, and certainly up here, it stops superconducting and just becomes an atom. If you look in the superconducting phase, most of the time, it looks like plain vanilla VCS. There's a tunneling spectrum, there's microwave measurements. Let me point out this one, which is kind of interesting. And so this is a plot as a function of carrier density of a whole bunch of lengths. There's the mean-free path, which is the longest. There's the coherence length, which is the next one. There's the penetration depth, which is the next one. And there's the interelectron distance, which is 5 minutes. Thanks. So this is telling you that, well, you know, it's not surprising that you'll see something which is VCS back because you're in some of this metal limit. There's at least one oddity, and one of the oddities actually is that there's a negative isotope effect. The negative isotope effect is very big. So that provokes then lots of stories. So you see
I bet you oxygen 18 has a higher TC.
it's the wrong way. So I decided not to put author names on this because that would take too many pages. I refer you to Maria's review actually to discuss this, which is really very nice. But there's lots of stories. There's stories associated with a couple of the longitudinal modes, which is clearly very strong. There's stories with ferroelectric fluctuations on a critical point. And then there are various attempts to couple to this soft EM, which is difficult to do because it's not dipolactic and therefore doesn't cut. There's a nice story involving matter effect from the co-workers. There's, if you like, something that I would call flexible electric, which is going to finite cube. And there's 2 phonon TR. There's another way of doing it. So all of these things are in principle plausible. Some more data. There's now a lot of data associated with different materials, some of which are actually polar. And the basic message of that is that this dome with carrier density doesn't really care whether you're on the ferroelectric side. There is strong LO-phonon coupling. And so this you can see, and so these are LO modes and numbers of shakeoffs. So this is from power Planck's group, this is from photo emission. So we know that that coupling is strong. That provokes a mechanism which has been around for a very long time. As the Hilbert plasma theory is Makada, 70s and 80s. And that produces a nice dome for reasons that are more or less obvious. And this dome here is produced by coupling to the mixture of the plasmon and the LO-phonon. Very few can argue with this theory. I kind of like it. It's actually not difficult to. It is in this anti-adiabatic limit. The plasmon frequency is bigger than the Fermi energy, and the Fermi energy is only barely bigger than TC. But I don't actually think that that's a problem, at least for theorists. It is a problem for experiment, because we've never been able to find the plasma. So this is some recent data from Premala's group. And so what this is electron energy loss, which is how we look for plasma fluctuations. So what you're seeing here, this is at Q = 0. This is at the zone boundary. This is all at room temperature. And here's a dope sample, Q = 0 boundary. Let me just talk you through this. This looks like what you would expect. There's LO modes and shakeups. A lot of LO modes, but there's a couple of strong ones. And these are the longitudinal ones. If you take the same sample and go to the zone boundary, you see basically the same LO modes. And then there's an extra one continuum. Maybe on
This is no zone.
You're going from undoped to doped right now.
Sorry, thank you. I want to go back to the zone boundary. Thank you very much. So there's an extra bump that appears out here. These modes are super sharp. And the natural thing to think of this actually is that this is some 2-phonon process associated with coupling to phonons to basically acoustic phonons upside down. And this is roughly the right kind of spectrum. I don't think it knows that. If you go down, however, what you should have seen, and what you would have seen, by the way, if you did this experiment in gallium arsenide, is an Nano-Phonon and a plasmon, with a plasmon with a very sharp excitation. They're both longitudinal modes. They hybridize, and you get an in-phase and an out-of-phase mode. But that isn't what you see at all. You see a bump. And by the way, the bump has the same spectrum as this bump. And then, when you go to the zone boundary, this bump just gets bigger. And by the way, the oscillator strength in here is roughly what you would have expected from the plasma, except that it's completely and it's somehow mixed. And there are various kind of odd things about this, is that you might say that I don't know. If this continuum is actually a broadened plasma, how is it that a longitudinal mode can run through it without interacting? You would expect to see at least final line shape. And there's none of this. So this is a problem. The bipolaron story has one piece of data I almost which is this is data actually from Jeremy Levy's group. These are samples which are LAO-STM, so these are in interface electron gas. And you basically made a structure with a small quantum dot in the middle, and you can tunnel on and off it. And you see these lozenges associated with this. They're associated with 2e. So 2 electrons come on and off, so you know that. And furthermore, they persist at temperatures well above HC2. So no. And then lastly, what I want to show you is that as you dope, the TA mode does stiffen. This. And this is a very recent paper from McLeod. And just to close with his punchline, which is that he can extract a length scale from this function. That length scale, which I'm plotting here, one of these things is this one. Actually, as a function of carrier density, this length scale changes, and he would like to argue that the peak in TC happens when 2KFL is a below 1. This is just an observation. I don't think there's any theory behind it, but I want to ask Steve about this. Okay, so there's my close, and we can kind of do kind of discuss.
Got a zillion questions, but let me start at the last one. I thought that they see quantum oscillations in the dope. So isn't that inconsistent with a bipolaron picture?
Oh yeah, I mean, I don't. So I think that I don't think. Well, okay. I mean, what I would have told you, since we've done ab initio calculations, really ab initio with bipolarons, is that it's very difficult to get into the regime where they're bound.
Okay.
Which is separately about that. So, and indeed, the quantum oscillations are very good. It's a very good metal. And as you saw, that the mean free path is extremely long.
Yeah.
So there's very little evidence for that, except for that one set of experiments from Jeremy Levy's group. But of course, that's a very different system from the box group.
Yeah.
There is also very strong evidence that we are in BCS regime.
Yeah.
The pair size is much larger than.
Yeah, that's basically what I would say. The pair size, right? So all of this really looks like BCS.
Okay, good.
Very quick.
Yeah.
Quick question. So in the very dilute limit where you have one pocket, what in your mind is the transport scattering mechanism? It looks like an ordinary metal. You have a tiny pocket.
Well, okay, okay, well, here's another conundrum. These are very good metals at low temperature. By the time you hit room temperature, they're very bad metals.
Well, okay, that's up to 80, 100 Kelvin.
No, right. And by the way, there are three classes of, there are three materials that do this right now, and they're all on the verge of being ferroelectrics. Strontium, titanate, potassium, tantalate, and tin telluride. They all have basically a T-squared resistivity, so the mobility is dropping very slowly. What's the mechanism for scattering? I don't know.
I think that needs to be understood.
Absolutely.
along with everything
All
else.
of, the- all
right?
of these things have to be figured out.
Just in relation to a Martin question, I think there is I'm sure Peter knows about it, but it's sort of glossed over. There are two different ways to dope carriers here. One through niobium substitution, another through oxygen deficiency. And it can be shown, and I think we've shown that with Kaman Beni very convincingly, that they do completely different games with electronic structure. And correspondingly, transport scattering and everything else should be dramatically different between these two cases.
So the system is considered to be very inhomogeneous actually at low carrier densities.
Eventually it is, but only at the very lowest carrier density. So at the very lowest carrier density, you see
Well,
a very large magnetoresistance, linear magnetoresistance, which is usually the kind of thing which is associated with the instance, right? But that's only in the very lowest carrier densities. Should be there.
First, one last question while Damjan says so.
So Peter, on the first part of the talk, there should be a phase transition to some sort of pneumatic or laminar phase? Is that,
I mean,
is that,
everything is a crossover.
why is that a crossover? Isn't that a broken symmetry state?
Well, because the symmetry doesn't break, because actually, I mean, you produce, it's lamella, but the lamella directions are fluctuating.
Why are they fluctuating? Then it's, once you form the amenal, it should be some sort of XY order parameter, so it should order.
You're asking about the ordering within the lamella phase. So there's a.
Just the orientations.
I think he's thinking about continuous.
I know, so there's an XY order parameter.
Oh, I see.
So it should have,
Well, actually, it's really an O3 order.
I thought that these were tetragonal.
Because of the tetragonality, that will break, right? So all of those, so if you go to, right, the question which we had earlier about, I pretended it was cubic, I wanted to ignore all of those
Yeah.
things, right? All of those things will break symmetries and there should be transitions.
Yeah. But there's no thermodynamic evidence of additional
There's no-
transitions.
You can ask people who will take data out of drawers.
Uh-huh.
and
So the
say,
answer is
"Oh."
maybe.
So the answer, I think, is maybe.
I see, okay.
Yeah, it's there's a sort of a lot of groupthink on various things, and therefore some data that people take, they don't really feel that they could get published. They can't publish.
Uh-huh.
So as I say, then you go and ask your friends, and no. The other question of this is on the magnitude of the flexoelectric coupling. I asked Harold, how big is it? And he told me, he said, well, what number would you like?
So Peter, this material also has this very large thermal Hall.
So the interest of time, let's move. Sorry to interrupt, but let's thank Peter Littlewood once again. So our next speaker is Damjan Pelc from the University of Zagreb, and he will be talking about the electron-phonon coupling in metals.
Thanks everyone for being here and for inviting me. I will basically continue where Peter left off, right? So given that we now all know everything about Strontium Titanate, I won't introduce it a lot, but I will mostly try to show some new, mostly unpublished experimental results that concern this electron-phonon in a bit more detail. Now, this is it's a collaboration of basically three excellent sort of postdocs, Avi, Maria, and myself, and being the only experimental point in that triangle, I'm at a bit of a disadvantage. But so far it's been working quite nicely. So Maria, of course, is here, and most of the dirty work is being done by two students. This is Noah, he's my student in Zagreb, and also Isam, who is here in Martin's group. And then, of course, there will be some neutron data that published. So, again, I'll basically do a very quick reminder of some things, but most of this you heard in Peter's talks. Now, one thing I would like to point out here is that so as Peter mentioned, there is a tetragonal transition in the system at 100 Kelvin, and then this splits this soft PO1. This splitting is usually ignored. For us, it's going to be quite important for the technical reasons and for fundamental reasons. But just keep in mind that it is quite significant. So at the lowest temperatures, it's about a factor of 2. This lower mode actually falls below 1 MeV, so it's really a super low energy. Of course, as we know, this is a material that's close to ferroelectric instability. It has this tendency for titanium to go off center. And yeah, as I mentioned, this degeneracy is lifting the trigonal. Now, this is a slightly different TC versus doping phase diagram. It's essentially the same as the one we saw in the last talk. There's 2 domes. The shape and makeup of these somewhat depends on the type of dopant. So again, only oxygen doped STL has this lower dome. If you do niobium doping, platinum doping, you only see the higher dome. But generally, the phenomenology is quite consistent. So even if you do oxygen doping, you will see the higher. And again, TC is quite high compared to the Fermi energy. In fact, here it is really high. Here it's a bit less high, but it's still very high. And yeah, most of this was discovered back in the 60s. And it's a bit amusing to me that I believe that most of the experiments that I will talk about today would have been done in the 60s. Of course, we'll never know. But yeah, we come to a point where we know enough to actually do this. Okay, and then the second important point is that there are actually 2 Lipschitz transitions. So the band structure has 3 bands. And this is due to a combination of this trigonal splitting and spin orbit coupling. So this in the slowest limit, you only have 1 band, then there's 2, then there's 3. And as you can see, this outer, especially this outer from the surface, is very far from the sphere. So it has this quite complicated shape, which again will be important for us as we move on. Okay, and then yeah, with doping, you basically move up to this band structure, and it is again mostly assumed that these bands are rigid. They don't change much. Of course, this also depends on the type of dopant. So the band structure, especially in the low side, is a bit different for oxygen than for niobium doping. Now, this is something I will mostly ignore for now, because well, one reason is that we will focus on dopings that are here somewhere. Here, the difference is not that big, but this is also definitely something to do. Okay, and then now strontium titanate has been studied for a long time, and there's been a lot of new results in the past decade or so. And I think it is generally agreed that this TO-phonon plays an important role. But a lot of things are not clear. So one of the things that really isn't clear is what the normal state looks like. This one question is the scattering mechanism that's still debated as far as I know. And the other question is the effective mass. So there's been some measurements of, so this is from Seebeck effect. You can extract the effective mass under some assumptions. And then what you get is that it goes up very quickly with temperature. So this is a huge mass enhancement. You go from 0 to only 200 Kelvin. So we go from something like 2 to above 10 M star. And there's been some thinking along the lines, and this has to do with polaronic effects. The Electron-Phonon coupling, which is pretty strong, that somehow these electrons get dressed more as the temperature increases.
If you don't understand the temperature dependence in the conductivity, how can we extract an effective mass from the Seebeck?
I know, I'm not saying I agree with this.
Okay.
As you will see.
Okay.
But yeah, this is
Moreover,
definitely
in interband gaps are of the same order, so it's really messy.
yes. I will get to that point. So, but yeah, let's say this is out there, and it's definitely a question now. What's happening? And then the second point that was also mentioned by Peter is so if you have the soft TO-phonon that seems to be important for superconductivity and also for the normal state properties, the question is how you can couple to it. And now, of course, the conventional linear gradient coupling is identically 0 for a TO mode, since these two are equal. No, anyway, this is 0. So that means you need to find other ways to couple to it if you want to see. So if this role is important, there has to be a way to couple. And now there's 2 options that I will discuss. that were also mentioned in the previous talk. One is this two-phonon mechanism, which is basically a square, displacement square kind of coupling. So this involves the exchange of two phonons. And this has been suggested way back in the 70s, but then recently it's been revived. And there's been attempts to explain both the normal state and this vacuum pairing. And the second is this spin orbit assisted coupling. Now, this is quite a special thing. It's linear in the phonon amplitude, but it involves the electronic states, the state cross signal. So this is a very strange kind of coupling, which I don't think has been directly observed. So basically now the question is, you have these two possibilities, which of them, if any, is relevant for the physics of the system? And this is one of the questions that we're trying to answer with what we're doing. And now, if there is this spin orbit kind of couplings, then there's been a recent prediction that this leads to spin phonon hybridization. So if you split the Fermi surface with a magnetic field, you should be able to hybridize with these spin flip modes. So there's going to be some sort of anti-crossing. If this is a spin flip mode and this is the TO mode, you're going to have a change of character at some characteristic field. Now this is the actual prediction for the low carrier density limit. And there's a lot of modes. So this includes LO, TO is here, and then this is a plasmon and two spin flip modes, and they all hybridize basically. So if you have this coupling, you're going to get this quite complicated hybridizations. And now also in the real material, there's an additional complication that it's not cubic. So these two, the purple and the blue, are actually split already, right? Crystal. So this scheme will look a bit different. But the main qualitative message here is that you should get some kind of effect, some kind of anti-crossing point, when the spin flip energy, so it's just the electronic G factor times field, is comparable to the TO mode. So this is something that's in principle experimentally observable, and it's one of the things that we wanted to see if it is possible to do. So I will talk about three different kinds of experiments which address some of these questions, or hopefully. The first is NMR. So we did NMR in the metallic state of Pelc, but we try to see with this microscopic technique what the nature of charge carriers is. Then the second is far infrared spectroscopy with somewhat new technique, where we actually see signatures of the spin phonon hybridization. So this should enable to extract the actual magnitude of this coupling. Then finally, neutron scattering, we were able to see phonon anomalies, which is something I'm quite happy with. But yeah, this also, in principle, should enable one to find what the coupling strength is. Okay, so the first thing is NMR. Very briefly, this is a very simple, in principle, experiment. You just measure the titanium NMR night shift. So these are the spectra. There's two isotopes. They mostly do the same thing. The lines are very narrow, so this is a non-pathological system in many ways. And the lines shift a bit with doping. And they shift a bit with temperature as well. And of course, the night shift is in principle proportional to the electronic spin susceptibility. So this is a direct microscopic measure of the spin susceptibility, which then can be connected to the effective mass and so on. And this is what it looks like. So what we find is that there is a strong temperature dependence, which is completely consistent with simple non-degenerate Fermi gas. So that's this line here. This is actually a full calculation, including all three bands and everything, done by Maria. So basically, this is as exact as you can be. And then the only scaling parameter you need to fit your data to this is the Fermi energy. So you can extract the Fermi energy from this measurement without any assumptions. And what you get is something that this Fermi energy is half the band Fermi energy. So if you do the band structure calculation, you get a Fermi energy. And what you get from experiment is half that, which means that the mass is enhanced by a factor of 2, which has been seen before at low temperatures. But now here we show that there's basically no temperature dependence. So you could not get a nice collapse like this if the effective mass were really temperature dependent. So the message here is that, yes, there is a mass enhancement, but it doesn't depend on temperature. So you just, yes.
Do I understand you're basically taking the band structure and squeezing it by a factor of 2 and then everything works?
Exactly. The main point is that it works at finite temperature.
Yeah.
This is a temperature that's comparable to the Fermi.
Mhm.
So it's not just a low temperature mass, it's across the whole. And this is a unique thing that you can get from NY. So it's a local susceptibility flow. Okay, yeah, this is basically what they said.
Could there be any enhancement in susceptibility, like stoner type? Because it's, after all, it's titanium 3D metal. It can be stoner enhancement.
In principle, yes. I don't think we thought about this.
It should be computable, by the way.
I think so, yeah. You can do an RPA. So this is just bare band, nothing. So, I mean, it's still a complicated thing to do, but it doesn't involve interaction at all. So, yeah, I agree. There could be some.
I mean, probably small effect, but then
yeah,
who knows?
But there is another interesting effect, which we only recently realized that exists. And this is that if you combine this spinodic coupling and trigonal splitting, there is an effective easy access anisotropy. So in the low doping limit, you can do a comparison to the Zondervold coefficient, which was measured previously by Chris's group here, through something that's called the Wilson ratio. So you can do susceptibility divided by gamma. There's a pre-factor that makes this 1 for 3 electrons. But then what we see in experiment that it falls below 1, significantly below 1. And you can actually reproduce this with this band computation, and you get this strong anisotropy. So basically the longitudinal susceptibility is nearly 1. There's a little minimum here, but the transverse goes down strong. So basically a combination of these two creates an easy axis. Yeah.
So is the dashed line a calculation?
Yes.
Oh, okay.
All 3 of these are calculations. And this is, so it's a multi-domain sample. So you're basically seeing 1/3 of one and 2/3 of the other. But yeah, these two are just 2 susceptibilities. And the nice thing here is that, again, there's one adjustable parameter to fit the data to the line, and that's the hyperfine coupling. The hyperfine coupling for titanium is known, and the coupling you need to get this is roughly aligned with this. It's not quite the same, but it's pretty close. So this gives us reason to believe that this whole story is essentially correct.
Are you sure that it's Fermi contact? Hyperfine field only. There should be dipole contribution, right? Maybe orbital.
It's actually something called indirect polarization. Yeah. So you polarize the s electrons by the core.
Yeah, that's core polarization.
Core
Yeah.
polarization.
Yeah.
And this is not.
And besides, I mean, you probably can have dipole contribution, maybe orbital contribution.
Yes. So this would go in the right direction. So if you take it, I don't know what it is, the number. So the core number is null.
It's computable.
Yeah. But if you take it into account, maybe it agrees in that. So essentially, this is in the right scale. Okay, and also you can see this in a very nice way by looking at just the matrix elements in the susceptibility. So here they're projected on the Fermi surface in this low density regime. And again, you can see that for the CZ, there's essentially nothing happening. So it's basically 1. But for the transverse one, there's this strong suppression. And actually, as you increase the EF, you can follow how this goes away because of the trigonal splitting goes away. So the trigonal splitting scale is 10 MeV, 100 Kelvin. Once you're above that, this anisotropy basically goes away. So this is really a consequence of this trigonal splitting. Okay, so to summarize the NMR, we have found that this electronic susceptibility is consistent in a wide temperature range, just with the non-degenerate Fermi gas. Which is in very good agreement with this non-interacting calculation, but which takes into account the full band structure. There's no evidence for temperature-dependent mass enhancement, and there's this interesting interplay that we found. So this would not be there in a cubic system. This is just the consequence of this thing. Okay, so moving on to the second part, which is the spin phonon thing. So to look at these phonons, as I mentioned, the energies are very low. So the lower mode is around 1 MeV, which is 250 gigahertz in frequency units. This is very low. So it falls in this dreaded terahertz gap, which nowadays what people do is they use pulsed techniques. So you can go to these frequencies, but the bigger issue is that the samples are bulk. So these are not thin films, and they have very high conductivity. So there's no way you can do a transmission type experiment. And the reflection coefficient is basically 1. So what we try to do is a slightly different method where we measure the absorption directly through the temperature of the sample. This has been done before, quite long ago. But yeah, here, again, it's kind of a revival. I think it works very nicely for this. And the second nice thing is the source. So it's not easy to get frequencies in this range, especially if you want to do a wide temperature, a wide frequency range. So what we found is this very nice thing where you have a diode, so-called mixer. So this is a special diode. You shine 2 lasers on it, and it gives you the difference between their frequencies. So if you have two lasers, you can control their temperatures. Through that, you control the wavelengths. You mix them with the mixer, and you get out a continuous wave sub-terahertz radiation. And this is sweepable in a very wide range. So right now, the system can do something like 50 to 800 gigahertz. So it's right where we want it. And it's also quite useful for a bunch of other things. Okay, this is what I mentioned. So basically, the thermal technique works, again, in a very simple way. You glue the sample to a thermometer, which is very sensitive. You modulate the light that falls on it, and you get some sort of modulated temperature signal, which you can measure with a lock-in. So this is all relatively easy to do. And the nice thing is that it's quasi-optics. So there's no transmission lines. It's just a light pipe, which is much bigger than the wavelength. And it essentially behaves like an optical spectrometer. Sensitivity is very high. And yeah, the special feature is that you can really measure absorption in samples that basically reflect everything. So if you measure absorption, that's 0.1% without too much trouble. And yeah, generally, so this is something that we developed very recently, and it's going to be useful for, of course, all other things. And my student Jakob, who's also here, has a poster. So if you have more questions on the technique, that's maybe a good opportunity. Okay, so now what do we see? This is now several doping levels. There's more data. I'm not showing everything. And the main message is that there definitely something happens. So what I'm plotting here is the magneto-optics coefficient. So this is the absorption in a field divided by absorption in zero field. So this is essentially 1 at zero field, and then something happens. So this big blue blob is at frequencies that corresponds to this lower TO. And you can see that as the mode frequency shifts in doping, then so does the blob. Now at this doping, there's very little left, at least at 12 Tesla. But there is still a little bit. So if you look at individual scans, you can see that something's. And basically, so just qualitatively, forgetting about everything, this means that there is definitely an effect of the field on the phone. So that means that there has to be some kind of spin interaction involved. What we were able to do is do these fits. So these are just simple heuristic fits of a Drude part, that's the red blob, 2 TO modes, and the spin flip mode, which according to this theory, when you're close to the anti-crossing point, the spin flip will have some phonon character. So there's going to be a phonon weight associated with it. So if you do these fits, you can pretty much reproduce what is seen. Now, yeah, there's a lot of points here. I'm not going to go through all of this, but the main point is that there is a hint that you really see this anti-crossing. So the spin flip, of course, you don't see the spin flip when it's far from the phonon. You only see it when it's close. But the most obvious effect by far is the narrowing. So this blue here means that intensity goes down, which if you calculate the reflection coefficients from the electrical functions means that the phonon essentially narrows. So and this is actually shown in the fits. So with these lines, the width without field is something. It's around 100 gigahertz here. And then it narrows by almost 50%. So this is a huge effect. And this narrowing seems to onset roughly around the center here. Now, in the theory paper I mentioned before, this is not in there. They just assume that the quantum is perfectly sharp, which is of course not the case. But here, yeah, we definitely see this. And the hope is that we can actually use this narrowing to extract the coupling. So again, to summarize this, I think this field effect qualitatively confirms, let's say, this idealization scenario, which means that this Rajba-like coupling is definitely there. The most important effect is this narrowing. And yeah, we're working right now, the theorists are trying to do calculations of this field to try to extract the Electron-Phonon coupling. So once we do that, we will actually be able to tell if it's big enough to cause the C. That's kind of it.
Excuse me, that's a quick question.
Yeah.
So the technique you are talking about, it's for Q equal to 0 mode?
Yes.
Or, okay.
So this is just light. I'm getting to neutrons right now.
Can I just ask a quick question? Have you done these measurements also as a reference on potassium tantalate? Because that's a system where we know there's strong spin-orbit coupling. It would be interesting to
Yes.
see as a reference.
The thing is that it needs to be doped. And it's very hard to dope. So now there's been some advance there and we're getting samples. This is in the works.
Okay, because that would be a nice
Yes,
contrast.
absolutely. Okay, so now the final thing are cone anomalies. And if you look at the Fermi surface, you can imagine various connecting vectors where you could expect a cone anomaly in the phonon spectrum. And now what the theorists tell me is that for intraband anomalies, they're only possible with a one phonon process. So if there's a question between one phonon and two phonon, you can only get these intraband anomalies with a one phonon. So they would again enable you to see this right now. And of course, this is known for a long time. The anomalies are maximized if one of the curvatures goes to 0 or infinity. And at the Fermi surface, there is actually a point in this outer one where that happens. The curvature goes from positive to negative, so there has to be a point where it's infinite. And this point corresponds to this A. But of course, there's other nesting vectors, and we can try to do neutron scattering and see if these anomalies are. And so we did neutron scattering measurements with very high statistics. So this was not a voltage in the triple axis instrument. This was a huge sample, and we counted for quite a long time. So we have really nice data. And however, it turns out that we didn't really need to do that. So one of these anomalies, this A, is actually huge. So this is what it looks like. On the right is just a simple, again, very stupid model just to show. So basically, you get this fall because of the resolution. So the actual phonon dispersion is convoluted with the resolution ellipsoid. That's where this minimum comes from. So this was just to show the effect of that. But essentially, you get this huge thing right where you would expect it. So we know the doping level, we know how long this should be, and that's exactly falling here where it should. So we were very happy to see that. But you can also see hints of two of these others. So there's an interband here. This is very low Q, so it's a bit hard to do the measurements. But there seems to be something happening. So this is now dispersion measurement very close to the zone center. And of course, this resolution ellipsoid integrates over a lot of stuff. But you can still see some funny things here. So there's a bit of a gap here. That's the most obvious thing. And again, the statistics on these measurements is huge. So it's really reliable data. So in principle, we should be able to do much better deconvolution. So this is just an initial thing. And then finally, there's also a hint of the C. Now, this inner Fermi surface has a much higher Fermi velocity, which would make the cone anomaly much smaller. But again, if you do a super good neutron measurement, then you can see maybe something happening. And again, this is an attempt to simulate this. And also, similar to the other ones, this is roughly where you would expect of the band structure. So we are pretty confident that we actually do see these anomalies. And again, as I mentioned, for this C and the A, they're both intraband. So they should only be possible with a single phonon process. Which again means, so first of all, this is huge. So it means it's partially huge because of this just the shape of the Fermi surface. But it definitely means that this large coupling is quite significant, and we should be able to extract the data. But yeah, it's quite nice that we also see these others, and it should be helpful to actually discriminate between one phonon and two phonon. Because also these interactions depend on Q. So it's, the large coupling is actually strongest here. It's very weak here. Of course, this interband can be caused by two phonons instead of one phonon. So there's a lot to do, of course, with these data. But the fact that this is observed is very nice. So now, of course, you can go to different doping levels, do the same kind of measurement and trace it with doping and so on. So now, I think for the first time, we have actually a method to extract these couplings. So again, to summarize the neutrons, there's definitely quantum anomalies, which again, these interband ones should be due to the large coupling, and it should be possible to actually extract, compare also to the magnitude of optics. So with this, I conclude and thank you.
We have about 7 minutes for questions.
A simple question. The quantum anomaly is expected if you have nesting and the band dispersion of opposite sign like this, but not like that. So that holds for your A and C, but it doesn't hold for your B.
Yes, not sure about B. So, I mean, generally.
So these bands are like this, so they will not.
Yes, I agree. I mean, there's also other possibilities. There's a vector that goes like this. So, you know, here you integrate over a lot of Q. Okay. So you can't really identify this one or something. But I agree. So this is, you know, it's more of a qualitative thing. So there's definitely something there, but you can't be sure that it's really this vector.
Yeah, a related question. What model did you use to compare the cone anomaly from experiment?
Oh, it's not a model, it's just.
But it's this model.
Yeah, okay, that's maybe not the best word. So all I did is I assumed a dispersion, quadratic dispersion with a step, and then convoluted with resolution. So this is just to see the effect of the convolution. So it's not really any kind of, you know, physical model.
Very nice stuff. I was just thinking, maybe I'm missing something, but I would expect that all these processes have to be what you're calling the Rashba, because the two phonon come, they interband with associated with the two phonon, the two bands have to have opposite parity, or it's actually two different orbitals, right?
Yes, yeah.
And here it's all d orbitals, right? The p orbitals are so far. So I think, don't you think that everything you're seeing has to come from that? From the coupling that is linear in you?
This is really a question for Avi, but yeah, I think they did some calculations.
Okay.
Very interesting data on the cone anomalies. I was wondering, you see an increase in the phonon line width?
That's tricky. So basically, the problem we have is this convolution. So we have to do an exact deconvolution to know. In fact, you can get this kind of step if you just assume that the width is much bigger.
Right.
So this is, again, this is just one of the possible. There's definitely something there.
So would inelastic X-ray scattering be a technique that could be helpful here because of the better momentum resolution?
I think in this case, it actually could. So of course, it's very hard to do measurements at one angle. That's
feasible. It's well, right at the limit, but
right. But yeah, I think here, so these are decent energies and Q is reasonable. So I think it could, but, you know, we have the neutron experiment, so this is one of the things.
Yeah, so to continue on this resolution thing, have you tried measuring on the other side about this focusing effect of the resolution?
So this is on the focusing side. On the anti-focusing side, you just get a huge block here, as you should. But it actually is inside me. Sorry?
What does the
neutron scattering? Don't worry about it.
Okay.
But you can explain it with the ellipsoid there, right? You
So
go to minus.
have the ellipsoid like this, or it can be tilted the other way. If you tilt it the other way, then it smears things out.
Yeah.
So it depends on which side of the bracket. But we actually tried all four. So we have these, and you can see this. So it's definitely there. All sides. But yeah, the resolution outside effect is huge.
Any other questions?
Yeah, so you use this, I guess, to extract the number for the Rushbrook coupling?
Not yet,
Not yet, okay,
but it's,
but it's coming.
and it's true.
I don't think I would ever see this, but we have more time for questions, so if there's nothing else.
It's too fast.
No worries, now let's thank Damjan. Here's that. That's you.
Okay, never mind, I'll use, is this just gonna do it?
Yeah, that's just.
That's fine, I can be folks. I'll do it this way.
Ready? Well, the last talk before the coffee break will be given by Premala Chandra, and it will be on the tunable spatiotemporal orders in driven terms.
All right, well, first of all, thank you very much to the organizers, of course, Ron and Martin, for inviting me to come here. It's great to be in Minneapolis when it's not cold and windy.
I would like to respond and say that the weather in March meeting was great, and we should have it.
You didn't do your full job. though.
I have seen worse here. So.
But Commissioner, when I come here in December, it is tough. Okay, even by Jersey standards. Okay, and also, I'm happy to see some old friends and hopefully to make some meetings. Okay, so there's.
Friends of long standing.
Friends from last millennia, like you and I. Right. Okay, so there's been a lot of excitement recently in driven condensed matter phases, particularly due to recent developments in ultrafast optics and to a number of theoretical proposals for very exotic non-quantum systems. So today, I'd like to tell you about some work that our Mary Yang has done in this area, led by Daniel Kaplan, who's here and did a lot of the heavy lifting and all this. Then with Pavel Volkov, Hannah Chakraborty, and Zekun, and I hang on to your life to keep up with these youngsters, but that's what it's all about. That's what it's about. Okay, so what is the question in these fast optical measurements? The question is, can we induce with terahertz light phenomena that's inaccessible in equilibrium? And what do I mean by that? Well, for example, I might have, heuristically, I might have a potential in equilibrium that looks like this, but in non-equilibrium, I can develop a metastable state that would not be accessible in equilibrium. Another possibility is that I have my potential energy surface here, and when the system is excited by this terahertz radiation, that I get order parameter oscillations and all kinds of things. Now, the question that our Mary Yang asks is, can we get tunable light-induced phenomena that's inaccessible. All right, so let's start at the beginning. Let me tell you about two lovely sets of experiments that motivated our research in this direction. The first is from the MIT group of Keith Nelson. And these were experiments on strontium titanate, about which thankfully my predecessors in this session have educated you all about, so I don't say anything about it. So as you know, strontium titanate is a system that's very close to being ferroelectric, but it's rebellious. That's why I like it so much. Okay, it's stubborn. However, what was done was that it has a polar mode that, as we saw from the previous talks, refuses to go soft. That's why the dielectric constant saturates. And what they did was they resonantly pumped this mode. And what the MIT group saw was that that induced a transient polar phase. Now, the work that was done in the Hamburg group, Andrea Cavallari and colleagues, is slightly different. What they did was they resonantly pumped a high frequency optical mode that was anharmonically coupled to the polar mode and drove it soft. Okay. And how did they know that they got them soft? Well, they looked at second harmonic generation. And that told them that in fact, the system had broken inversion symmetry, and since strontium titanate is really well understood, that meant that they had actually had a light-induced ferroelectric transition. Now, more recently, these are terahertz pulse probe measurements. More recently, people have developed ultra-fast time resolved diffraction measurements. And in fact, in his talk, Peter showed us one from the Ornstein et al. Slack group, where what they're able to do is within a pulse width, that means within 10 to the minus 12 seconds, they're able to take a snapshot and look to see what the structure is. So that's how people can characterize that now. So these are the sorts of measurements that inspired us to think about light-induced phenomena. So let me just give you an overview of what the key idea is. The key idea is in many ways a many-body generalization of optical tweezers. But what happens in optical tweezers? In optical tweezers, the light creates an effective potential, a change in the effective potential that's related to the atomic polarizability. Well, that's very similar to what happens in a light-induced phase transition. You have an effective potential, and for example, if you have the anharmonic coupling, let's take Cavallari's example, you have the anharmonic coupling to the high-frequency mode, and that high-frequency mode is resonantly pumped, then when we look at the effective potential, what happens is that we get a new term. This is the bare mass, and here we get a new term that's proportional to the fluence, E squared. And so we get a mass that's a function of the amplitude of the electric field. And eventually, because this comes in with the minus sign, the mass goes soft, and we get a polarization. Okay, so that's the key idea. And then what one can do, so we have a phase transition as a function of fluence. Let's just get a sense of how that works. We have an effective potential that has a renormalized mass term plus a p to the fourth. P is just our order parameter here. Now here's the polarization. This is the bare mass. This is a classical contribution due to the anharmonic coupling that gives us this minus chi E squared. And then you can even ask about quantum fluctuations, which of course should act in the other direction. And what you end up with is you end up with phase diagrams because paraelectric, then you have a softening into a light-induced ferroelectric phase. And in fact, if you go up in fluence, you can actually get an oscillation back and forth, and you can even get chaos. But we were very excited about that at one point until Andrea told us that the sample would break down long before we ever got there. So a different kind of chaos. Okay, so that's probably not on the cards for the moment. But in this sort of approach, the material has to be close to immiscibility in equilibrium. The nature of the ordering is determined by soft modes in the equilibrium system. Okay. So you can drive something that's already there. You might be able to change the structure a little bit by playing with polarization and stuff like that. And the characteristic features are generally not new. Namely, if you have transient order, it's usually commensurate with the underlying bias. So normally in this sort of picture, what you get out in this driven system is similar to what you might get in equilibrium with a couple of extra bells and whistles.
Right.
Yes.
When you say that is stable, does it mean that the moment I turn off my pulse, I go back to? Because I remember there was some claim that you would remain in the ferroelectric.
You're completely right as always. Yeah.
Eh,
Don't let it get to your head. We'll bash it out later. Anyway, I'm just kidding. You're 1 out of 2 right. In the MIT experiments, as soon as you turn it off, it goes away. But you're completely right about the capillary measurement. When they turned it off, it stayed for a while. And they actually attribute it to the kind of flexible electricity here. Okay. All right. But as I understand it, it depends on details of the measurement, and I'm not going there, but you're completely right as always.
1 out of
You're my host, I have to be nice.
I'm not.
Sorry, Kurt's my host, but
Run.
he told me I had to be nice.
Okay. I didn't. Why would I do it?
I have to curry favor so that if I run over time, I can do good ones. Turin was my neighbor at Rutgers for a long time.
Sorry.
That's not. Right, maybe you ruined.
He doesn't deserve it.
All right, so now for something completely different. I'd like to tell an alternative pathway to light-induced phases, which is quite different from what I just discussed. And indeed, I'm hoping to share with you a mechanism for inducing suitable spatiotemporal ordering in opportunities. Based on the interplay of nonlinearity, parametric resonance, and spatial dispersion. So what I'm going to do for the moment is I'm going to just give you a brief overview of the conceptual components of what I'm going to talk about, and then we'll work on a concrete example. So let me give you the conceptual components. Suppose I resonantly drive a high frequency mode, okay, like in the capillary region. Okay, so once upon a time, I have 2 modes, a high frequency Q mode that is accessible by optics, and a low frequency Q mode of vector mode. Okay. Now, I'm going to resonantly drive high frequency mode, and if it is anharmonically coupled, in particular with this cubic coupling here, to the low frequency mode, I'm going to induce a parametric response. Now, when I induce the parametric response, I get a mode activated at the driving frequency over 2. And because of the dispersion of the low frequency mode, I will get a modulation at some finite Q vector. And the modulation will be tunable by changing this driving frequency. Now, the onset fluence for this will be determined by the width of these modes. Okay. Now, if in fact I get this mode at Q0 and omega over 2, that due to nonlinear self-interactions can actually generate higher order modes, and in fact, it generates a static mode at 2Q0. So in keeping with the spirit of this conference, I should say that there will be a signature in time resolved diffraction measurements. And in fact, what I expect is that at Q0, the modulation that's tuned by the dry frequency over 2, I will get a spatiotemporal mode, okay, that will be intense. We'll have a period of, it will show up as a frequency of omega over 2. Okay, so it has a period of 4 pi over omega. And there will be much less intense static mode at 2Q0. And these are both modes that are completely, that are very different from what's going on in the current equilibrium. Okay. So now let me tell you, let's talk about a concrete example. Let's consider a polar system. Okay, so I'm going to consider a well-defined polar system, barium titanate, lithium niobate. I should mention, by the way, that I learned about barium titanate and ferroelectrics actually working at Bell Labs with Peter Littlewood, who was my mentor when I was a summer student. And look at us, we're still working on ferroelectrics. Okay, so anyway, so thank you, Peter, and you know who to ask if they're getting something wrong. Or Daniel. I take no responsibility. This is the modern way. Okay, so let's consider a polar system. So what's our action? Okay, our action is we're going to have just a vanilla Lagrangian. And here we have to put in our dispersion. This is our dispersion of the P mode. And we have the nonlinear self-interacting parts. In order to get this alpha PP cubed term, we need to have a system of very low symmetry. So for example, rhombohedral barium titanate, monoclinic, lead titanate, something like that.
So you're writing the symmetry broken phase.
I am deep in the symmetry broken phase. Deep, very different than so I have a finite frequency mode. I'm deep in the symmetry broken phase. Okay, I am a ferroelectric. And I'm cold. So I'm ferroelectric. And of course, I can just go back and forth between P and Q to get this. Now let's talk about the interaction between P and Q. Even though we're in a polar mode, polar phase, I'm going to be a little bit gentle. In an insulator, in an insulator, all these terms are finite. Okay, that would be a mess. Yes.
If we are in the broken phase, why there are no linear terms in P in the previous slide?
Pardon me? Well, okay, I can absorb the linear terms. So that just leads to a shift, but you're completely right in the beginning. Okay. And in fact, here's a linear term. You were ahead of me. Here's a linear. So here I have my coupling to the field. Okay. Here's a linear term between Q and P. I'm going to absorb that into this term, and I'm going to set my effective Z to be. Okay, so I'm just shifting. But thank you for the question. Now, if I have inversion symmetry, then these terms are 0. And I have a term that looks a lot like a term that Peter was talking about before. Okay. However, I'm in broken inversion symmetry. I have a polar axis. So for the moment, this is a subleading term. Okay. I'm going to align my electric field with the polar axis. And because I'm going to be resonantly driving this term will not be important because it's going to be a very high frequency. And we're not interested in what's happening. Remember, we're interested in what's going on below the drive frequency. And so we're not going to worry about this term. We are going to worry about this cubic term. And that's why it's so important that we're in the non-symmetric state in the polar state. But I will come back to this term, which looks a lot like Peter's term a little bit later. Okay. So what I'm going to do is I'm going to align my polar axis with the electric field. That makes that this is just gamma, and the other term is 0. Okay, so now let's look at our classical equations of motion. Okay. And in particular, you'll notice that I put in a dissipation, that's by hand. So we put in a dissipation. Dissipation, we couple the system to a bath. We put that in with isotropic damping. We also put in temperature with Langevin terms. And now our next step is to look for solutions of P and Q. Okay, so let's first do this numeric. So let's look at numerical solutions where T equals 0, and we're going to assume that those self-interaction nonlinear terms are effectively 0. They have to be very small just to make sure that we can have regular solutions. Okay, and so what do we see? So what Daniel has done is he's taken our initial P's and Q's from a uniform distribution with 0 initial velocity. He's done the calculations using the standard Langevin techniques. And he assures me that because of the structure of his solutions and his equations, that they satisfy a criteria which tells us that the integrability is all stable. So at low fields, so E less than EC, what do we see? What we see is that the solution, and this is real space, this is a function of time, and this is on the lattice, of course, okay, it decays exponentially. Okay. So we have it decays exponentially. But now we see that if we raise the electric field, what we get is this checkerboard pattern, and we see we have some ordering. Now, of course, a lot of information, as we know from our scattering codes, a lot of information is stored in the structure factor, in particular about the interaction between the modes and the dispersion. So what happens here if we look at the log of the structure factor? Well, if we look at the log of the structure factor, what we find, we see this dispersion. And that's it. But what happens for E greater than EC? Well, that's quite dramatic. You notice this is a logarithmic scale. So, and what we see is this parametric resonance. This is omega over driving frequency. This is exactly a half. And we see we have this very striking feature. Okay? And everything else is really without. Okay? So we have what looks like something like parametric resonance. Now, if we average over all initial conditions and look at this mode, P of Q and omega over 2, as a function of E, we see that it looks like it has a continuous onset that looks square root-like. Okay? And in particular, if at late times we look at the structure factor, at late times if we look at the Fourier transform, what we see is that for E less than EC, we have nothing, whereas we have these strong features here for E greater than EC. Right? And again, this EC seems to be a function of the width of the modes. Now, what happens when we put on our nonlinearity? This comes in as a P cubed term. So again, it only works in the system of parallel symmetry, like rhombohedral Titanate. What happens then is, in addition to our parametric feature, we get a static feature at 2Q0. Okay. And what's interesting is it's significantly less in intensity, but if we look at that feature, it seems to scale linearly with our original parametric resonant mode squared. Okay. So that's what we have. Now, inspired by these beautiful numerics, we decided to see whether we could understand the system using just three dominant modes that the numerics told us. Okay, so what we do is we take an ansatz where we're on resonance, and we're going to look for solutions of the form Q0 and plus or minus omega over 2, omega of the derived frequency. Okay, where Q0 is not 0. We look at the equations of motion, again, we're at resonance, and we define this detuning expression, where you notice that if this were 0, then we would be at resonance. Okay. This is the dispersion, and this is the resonant frequency of the self-harmonic. Okay. And what we're asking is, if we look for these solutions, do they enforce this resonance? Well, we plug them into our equations of motion, and we get this. And now, because we're at resonance, Q is imaginary. We're at resonance. And it turns out that the structure of the equations gives us a form like this for P. And at t equals 0, the initial phases are set. The phases are set by the initial conditions. So we can decide to set the phases at 0 and 2 pi, which means that this has to be pure real. Well, if this is pure real, this is imaginary, this guy better be 0. Okay? So as a result, if this is 0, well, that gives us a condition for Q0, which, as you see, is going to be a function of our drive frequency, omega p, and the dispersion. And if we plug that back into our equations, what we get is that we have a fluence that is inversely dependent on the coupling and proportional to the dissipation. And that makes sense, because if the dissipation is 0, then it should show up right away. Okay. And the higher the coupling, the lower the 0. And this is what we get also for this value of. All right, well, this is then a threshold fluence. And if I take my calculation and this calculation and compare it with the numerics, you see that it's actually pretty good. And indeed, what Damjan assured me is if it takes longer and longer iteration times, it actually gets better and better and better. Okay. Now, you might say, wait a minute, you have a new mode. It originates from this vertex. What kind do I have? A mode softening? What's going on here? And in fact, what you can show is this vertex should couple to the static mass. However, I have to go into a rotating reference frame. Okay. And in order to go to a rotating reference frame, then I get in a rotating reference frame, I get the static term. And you see that this is my first term, this is the bare mass, but here I have this other term. What that tells me is that I have a condition for mode softening, which again, not surprisingly, tells me about the importance of the amplitude of the resonant drive and the nonlinear current. Now, what about the leading nonlinear self-energy term? Well, once I have generated this parametric mode, using this leading nonlinear self-interaction term, I can generate a P of 2Q0 and 0. These P's are real. And so I can get a dynamically generated static mode. And indeed, if I plug through the equations, I actually find that this modulus is actually proportional to the modulus squared of our parametric mode. Minutes. Okay, I'll speed up. Remember, you were my neighbor once. I spent some time mentoring with your colleague. So let's just try for that, right, Raphael?
Yes.
And he can tell me anything you keep, right? I mean, it's always fun to banter with her. So I get this dynamically generated code, and this is very simple. Okay, important question. This is related to a question that Igor asked this morning. If I want to make contact with the experiment, I better know what's going on at finite temperature. Okay? And to make a long story short, what we find, we sort of held our breath because we all grew up learning about Hermann Wagner. And the question was, what happens if we put in temperature? Well, it turns out that if the temperature is of order, until the temperature is of order, the bandwidth of the low excitation mode, nothing happens. And I remind you that this is a classical problem. So the temperature goes like omega p squared times p squared. This is classical, just like a classical oscillator. So you notice, and we know this goes like this, you notice that this is really, this is robust, and yet when we go of order the bandwidth, it's fuzzy. And so you can look at the phase. Remember, the equations don't tell us anything about the phase. And the question is, why doesn't the phase just blur out completely? The phase only blurs out at higher temperatures, and you see these are our parametric modes. It's only at higher temperatures that they start to blur out. So we don't completely understand this. There are two possibilities. One is the suppression of fluctuations due to nonlinearities. This is believed to happen in, for example, models of flocking of birds, Titanate 2 model, or also in synchronization models, Raymond model. The other possibility is that you have very long conformalization times, but given the fact the experiments are on some finite pulse width, you don't think that will be a problem. Okay, so let me just get to material candidates, polar materials with low symmetry states. We wanted to put in some numbers, lead titanate, we have Q0, the numbers were, we had the coupling, we have a reasonable electric field fluence to get this, we have a reasonable Q0. We actually think for lead titanate, the modes are both longitudinal. We actually think that you can have an enhanced coupling if in fact the modes involve the same atom. Okay, and I'm happy to talk about this more, but that's something that we would like to explore. Now, just to connect a little bit with Peter's talk, in non-polar systems, okay, can you get this? Well, in non-polar systems, which maintain inversion symmetry, these terms will all be zero, but now comes to the fore this term here. And as I understand it, if you have a frozen Q here, this is called a invariant. But in any case, what we learned is that if you have the Leszczynski-Maria interaction, and you have a coupling to a phonon mode Q, that we can actually get something like this. And in fact, the idea would be that you would pump the buffer atom here, and you could have some coupling. And we're very excited about these possibilities. Of course, the couplings have not been calculated, and certainly not measured at all. But looking at the energy scale, candidate materials of legal oxide or chromium triiodide that we heard about in Marcus Min. Okay, so summary and outlook. We have come up with a new mechanism for driven tunable spatiotemporal orderings. Parametric resonance is by no means new. It's in the first couple of pages of the mechanics book of Leonard Lipschitz. However, I think what our contribution to this is to show that driven nonlinear phononics can actually lead to parametric resonance in solids, macroscopic solids, and that this can lead to a tunable spatiotemporal order that actually where the dispersion and the dry frequency set the modulation. Okay, of course, electric fields are uniform. It's very difficult to transfer a finite momentum to a solid. So this is a direct way of generating finite momentum ordering with light. It's a continuous onset as a function of fluence. It's amazingly robust to temperature. That's something we want to look at more and understand. The predictions for time resolved Bragg diffraction, and we believe that this is applicable to polar materials and also to iron ferromagnets with Maria interactions. So some things for the future. Characterization of the onset. We're hesitant to call it a phase transition because, of course, we don't have the equivalent of a free energy or anything like that. The phase looks a lot, smells a lot like a Goldstone node, but we don't know if that's actually the case. We have to do more calculations. Late time dynamics. Why is the temperature, why is it so robust at temperature? Is it just that it takes a long time to equilibrate? Or is there some reason where the nonlinearities are cutting off those fluctuations that normally give us Merlin Wagner? Then we're beginning a detailed search for candidate polar and magnetic materials. And I spoke to talk to many of you about this. And sort of more fantastical, could this approach be used to generate tunable nanoscale periodic potentials, except even for lithography or something? And also in the magnetic era, in the magnetic arena, could we generate localized magnons, for example, for nanoscale magnetic computation? And I think Turan is getting impatient with me, so I will. Thank you.
We have time for some questions.
That's on your last slide, you were suggesting search for polar materials. It might be off the range of what you're talking about, but it just comes to my mind that in titanium diselenide,
Yes.
there is actually several observations of transient chiral state induced by light pumping.
I see.
And I think we understand what's going on, but don't understand why. We did calculation, there is a ground state which is measured experimentally, which is non-chiral. But then there is another structure which is very close in energy, and it's chiral, and the energy difference gets smaller with temperature. Now, on the mean field level, in the calculations, this chiral structure never wins, but maybe it can win on like order from disordered level.
That would be quite interesting. Perhaps we can talk a bit more
Yeah,
about
okay.
it. I'm not so familiar with that, but let's talk for sure. Peter, hi, Pete.
Lovely, thank you very much. I suppose a couple of. You know, one comment about sort of related optical systems where people have done things like this. You can pump magnons this way, and people have used that to make things that they like to call magnon condensates.
Yes.
Which you may have seen, which is right. And the thing which is interesting to tune that is it's nice to be able to have your the double. If you go back to the previous figure, actually, just to show that.
Such a nice figure.
The dispersion there, you've actually got that the two modes at omega over 2 sort of rather usefully associated with some change in the dispersion.
That's exactly right. And what we need, and I didn't really emphasize this for the materials, we need two modes that are anharmonically coupled, preferably cubic.
Right.
And I need the window of opportunity within the bandwidth of the lower mode to pass the upper mode.
Yeah.
So,
I mean, but if you hit the inflection point there, you should get a much stronger
here,
effect. So the point of inflection in the lower dispersion, right?
here.
Yeah, because then what happens is that mode, of course, has the opportunity to elastically go to Q equals 0 and a signal
Yes.
idler.
Absolutely.
And usually the effects get very strongly
And
enhanced
in
there.
particular, if one could choose the numbers right, and this is why we have to do a concerted search of materials, then we're going to be able to move this up and down. The drive frequency over 2 up and down to exactly access different parts of the dispersion.
If I can follow up,
Sure.
maybe I'm wrong, but I think I remember that one of these magnons, the magnon dispersion actually has a maximum at Q, is the same branch essentially.
Right.
Oh, I
So
see.
I think in that case is because you have just a magnetic field or something?
No, yeah, but that's basically long range interactions.
Yeah, I wonder whether here you could, there is a situation where the mode itself could develop this, and maybe it's the hybridization, I don't know, but whether you could,
So you want, what you want to do is actually do something like this.
you go like this and then there's a.
And the point is that if you do that, then actually you can
You're-
even thermalize it that way,
Right.
which is why people then talk about it actually generating a VC.
Okay, that's very interesting. We haven't pursued that, but perhaps we can talk more.
Perhaps one last question.
So why isn't this spatial dependence of the pair characterized by zero?
So the only way it would be zero is if this omega over two coincided at the bottom
No,
of the band.
aren't you conserving,
We're conserving.
aren't you conserving crystal momentum?
Well, because we have zero here and we have minus q, zero
Yes, and they have
plus
zero.
zero. Yes, so we're conserving momentum. But the point is, if this omega over two were fine tuned to be at the bottom of the band, then we would have a modulation. But if it's not at the bottom of the band, then the dispersion will tell us what the Q zero is. I hope that answered your question.
Well, let's thank Premala once again.
Three 35, right?
So we will be back at 3:35. You know, it's getting. Yes, that's very cool.
So right, left, because you can basically have something which has a weird dispersion.
Think of the exactly simple.
But then it's not a bit easier because everything in the carrier is on the wavelength of flux.
So when you have it, they all are here. Now,
I'll be here until.
if it is chiral system and you can have level varieties.
Yeah, I know.
I do.
No, I really want to reach out. Yes, there was a talk, I think, at the.
The same extension. I was trying to learn. So I don't know.
Find out.
Yeah, you can see in right and right left, and it's identically the same.
Same energy, different intensities.
So it's in right in. So now why? Why is this correct?
Point is about intensity, a little bit of all of those.
Oh, okay, so maybe.
Okay, that's my thing. I thought that you said one about in I saw right and right left and completely different.
There's a.
It'd be nice.
But when you,
That's a key point.
the energy of this
Well, maybe there's some, maybe a basketball.
yeah, I mean, very much simple. I kind of.
Like these claims of like chiral.
Yeah. I saw that you really see something.
Wait, but that is not individual channel. Yeah, no, I already made you. But when you see two. Correct. So.
玩的什么那个都很好，然后到这个如果你的火接了，就送上去，到人家是有区别。
Let's take your.
Second, well, I never, like every time I switch. I'll be able to. Hopefully, going next.
Then I'm puzzled.
That's the initial.
But then it's in.
I have all of the channels. But it's so you I know, let me test.
飞上涨了有飞上涨，涨买什么都有。然后它在反正在那个档上，在对着涨完以后，
You want to end up using at least the.
Those traces, then it must mean that there is no mirrors.
No, in order to have parallel, you don't have mirrors.
In order to have an optimus, Raman optimus.
That's all true, but you are saying more than that.
But high pressure.
No.
That's right.
Yeah.
So, make sure we're talking about the same thing.
Yeah.
Not at all, not at all. I like it.
I love your super.
Wait.
She has a poster of super conductivity. I thought that was great.
That is.
I mean, but I wonder, I hope you don't want it all done in.
Oh, really?
More like my point.
I don't know.
Oh, yeah.
Okay, welcome back everyone. So this is the last session of the day. And our first speaker is Ray Osborn, who is going to tell us about the role of structural correlations in electron phase transitions.
Hello everyone. So thank you to the organisers for the invitation to the fascinating workshop. It's great to have a chance to see the real centre of Minneapolis. The premise of my talk today is that over the last 10 years, there's been a transformation in our ability to measure structural correlations, both short range and long range, using supercritical X-ray scattering. And I believe that that transformation makes a method which has been around for a while, something that's and which is intended to be confined to material scientists, sort of ceramics or superionics, and of much more interest to people who are interested in strongly correlated electron systems, or what we now call quantum materials. And so I want to describe that, and I'm going to give a kind of a whistle-stop tour through a few examples of the types of analysis you can now do with the new methods, which were completely impossible before. So, so actually, it's not the technique that's new. It's actually a fairly traditional technique for measuring supercritical fraction. You put a sample in the beam. You put a sample in the beam, then with an area detector behind it, then you will be sampling a section of the Abel sphere, you're setting a number of Brillouin zones.
you then rotate the sample, you'll be sweeping that A-bar sphere through reciprocal space, measuring a large number of those zones. What's new is that we now have much better quality area detectors, and we now have the computational power that allows us to cope with the large data rates that are now possible. So for instance, we can collect something like 3 terabytes a day. We collect a full volume in just 20 minutes or so. And to give you a flavor of what that volume involves, you know, this is actual scattering from measurements. We use 87 kilovolt X-rays at the Electron-Phonon source. That means we're measuring over about 15 specific angstroms in all directions. And that means that's an awful lot of Bragg peaks. It's thousands of Riemann zones, sometimes tens of thousands. And we're measuring it with a fine HKL mesh in all of those zones. So this is a large amount of data. A lot of it's very pretty. It all looks extremely different from one another. In the ways to solve these, you have to start afresh with each one. And so this is a bit of a challenge. And so although we've now, I think, solved the problem of being able to take that data and converting it into SOQ, actually in as much time as it takes to do the measurement, what we really now need to do is to try and ensure that we're not just looking at some tiny fraction of the data. We're not just looking at a few slices and trying to draw inferences from that. We want to use the entire data collection. And one thing I didn't mention is that because it's so short, like of the order of half an hour to do a single measurement, sometimes it could be even shorter now, then you can measure lots of temperatures. For instance, in the morning, you can do 10, 20, 30 temperatures, allowing you to measure all the structural correlations over the entire phase diagram of a set of materials in just a few days. So how do we ensure that we're using all the data? We have two approaches, which I'll describe here in the talk. One is machine learning, and I'll go into that later. Machine learning allows us to sweep through all those temperatures and extract useful information from them. The other technique is multidimensional spectral analysis, basically creating pair distribution functions in real space. And you're using all of the data because you're Fourier transforming the entire volume, scattering, and thereby condensing the data into sets of interatomic vector probabilities that are much easier to model. Okay. So here's an outline of my talk. I'm going to give, as I said, 3 examples. One is a study of the McLeod transitions in VO2. Another is what we call hidden order in Renate. And finally, Bragg glass phase in Telluride over palladium. And I've chosen all these because they illustrate different types of analysis that are now possible if you have the kind of large data volumes that it is now routine. Right. Now, of course, this is I've depended on a lot of collaborators. My partners in crime at Argonne have been Stefan Rosenkrantz and Matt Krogstad. Matt is now an infant scientist at the APS, and I encourage you to get in touch with him if you're interested in these techniques. He runs on the beamlines that implements them. We've actually also worked with Mike Mullen on some of the theory. The spectral analysis, we've worked with applied mathematicians at Argonne, Carl Haling and Ionescu. The machine learning comes from some very exciting ideas that came out of Cornell from Poona Kim, her current postdoc is Krishna Malaya, which have really worked remarkably well. And the example I'm showing involved collaboration with Jared Allred at Alabama and Ian Fisher and his group at Stanford. Okay, so let's start with VO2. And before I actually go on to VO2, let me quickly mention and describe the what we call 3D PDF in case you're not familiar with it. You know, crystallographers have for a long time transformed data from reciprocal space into back into real space to create Patterson maps, and they use that to solve crystal structures. Patterson maps are just sets of interatomic vector probabilities. Yeah. And what a group at Zurich realized, Thomas Weber and colleagues at ETH Zurich, was that if you could separate the scattering into a component from the average structure and components that represent deviations from the average structure, if you Fourier transform that, it remains separated. Okay. So can we do that separation? Well, of course, it's quite trivial because we know exactly where the average structure is encoded. It's encoded in all the bragg peaks. So we just get rid of all the bragg peaks. Now that would generate Fourier uptakes, so you paper over the cracks. And now we have essentially just this this quantity here, which we then Fourier transform. This whole process is called punch and fill. And we now implement that on a routine basis. And to understand what you can learn from that, if you transform data across, you can get these complicated distributions of diffuse scattering intensity over Q space, which just don't mean anything if you look at them. You might see a few features that you think you understand. They get transformed into discrete sets of intraatomic vector probabilities that correspond to intraatomic vectors in the crystal structure. And indeed, you filtered out all of the average vectors, so you're left with only those that differ from the average. And in this case, for example, as a simple example, this is sodium interpolated B205. The only disorder is then in this partially circulated ladder, set of penetrating ladders. And so the only features we see come from the ladders. And if you take, if you look at the probabilities, you see blue peaks. That means, so all crystallographers can tell us is that there are these two-leg ladders, like these, oops, I didn't do that. There are these two-leg ladders, and that the sodium sites are occupied with 50% probability. Okay, that's what you can determine from a crystallographic analysis. You can't tell what the local correlations are, but with a Excel PDF you can. I'm pressing the wrong button, sorry. Use this one. Wow. So for instance, this nearest neighbor vector is blue. That means it's less probable than the average, whereas this next nearest neighbor is red. That means it's more probable than the average. You get these three-leg ladders in PDF because we're summing over the probabilities for all the vectors from all the origins. So you can have the origin could be on the left leg next to the right leg, or it could be on the right leg next to the left leg. But what this means is you can actually read off the correlations without doing any modeling. You literally see that there are these zigzag correlations along the ladders, and you can tell, for instance, that the neighboring ladders are in phase. And indeed, you can determine correlation links for those precisely without actually having done any modeling at all. So what about VO2? So VO2 has a retard structure. We have these edge sharing octahedral on the c-axis, which are coupled along the 110 direction by these quantum sharing oxygens. And if you go along in that the 110 direction to look at that coupling, what's known to happen, so VO2 goes through a first order phase transition, as many of you will know, about 340 Kelvin. And what happens is there's a dimerization of neighboring vanadiums here. That forces out this oxygen, which creates a buckling of the neighboring chain of vanadiums. And then that pushes the this oxygen in, which pushes the so you still get dimerization here, but it's out of phase. Okay, so you have this alternating dimerization, buckling, dimerization. Okay. But in pure VO2, that happens simultaneously along two 110 directions, 110, 110. And that means that actually every single chain is both dimerized and buckled. Okay. But it's long been known that there is an M2 phase that you could induce by transition metal doping, where you actually remove one of the directions. And in this phase, you only have one chain, half of the chains are dimerized and half of the chains buckled. Okay, so this was fed back in 50 years ago. This fed into the whole debate about Mott versus Files for what's driving the transition. So Bob Carter's group were interested in what happens if you dope with molybdenum, and you can suppress the transition a long way. It persists up to quite high concentrations of molybdenum. But in particular, if you go out to 17% and 19% here, you see you still get first order electronic phase transition. It's now more metal to metal, but it's nevertheless you have these first order phase transitions at 17%, another one at 19%, etc. What's happening structurally in this material? Well, turns out that you get something rather more dramatic. This is the 70%, And here you see superlattice peaks, which are characteristic of the M1 phase. So bright peaks are the long range order, that are forbidden by the pure refile structure. As we see, you go up to 90%, but remind you, you still have a first order electronic phase transition here. You've no more bright peaks. You just have these rather wavy rods. Keep on doping the become increasingly diffused. And indeed, the rods become something like an order parameter. Okay, so they're very weak above the transition, they're much stronger below the transition. You can actually track them that way. What's going on? But if you convert it to 3D PDF, you can see immediately what's going on. You can see the origin of those rods. And that, the origin is, well, if you look at the M1 phase, you have essentially long range order. You see, we haven't punched out the M1 peaks here. We haven't punched out the superlattice peaks. So we can see long range order. These are all peaks that arise from distortions from the refile structure in the M1 phase. Okay? And they persist over very long distances. In the 19%, we now only see these correlations along in two-dimensional planes, one bar and one bar. Okay, and in fact, we only have a finite correlation in keeping with it along the one directions around 50 angstroms, which is determined by how the peak intensity is exponentially decay, and it's only about 10 angstroms transverse. So we have these quasi 2D planes, and to understand what those planes look like, we have to go along the planes. If we look at the 3D delta PDF, we get what apparently is a very complex pattern, but again, they are discrete interatomic vectors. And just as in the sodium and Titanate B205, you can essentially read off what's going on in the structure just by looking at what connects the red peaks and ignoring the blue peaks. And so you can see here, this is the crystallographic structure for what you get for an M2 phase. Here are two dimerized vanadium ions, and here you can see the buckled chain next to it. And indeed, we see exactly those interatomic vectors. We should see shortened vector here, so this along the z-axis, and we see this extra buckling of the vectors along this direction. And you might argue that I'm missing out this position here, and that's because we're summing over all of the possible sites in the system, and so there are. So we have to consider other vectors. Oh, okay. So I forgot. I was going to put. You can actually just overlay the crystallographic structure on the PDF. And see the result. But yeah, the extra red peaks come from choosing a different origin, as you can see here. Okay. So what we have is a strongly first order electronic phase transition. We have local lattice distortions that accompany that transition, but they never become long range. They only remain short range. And there's actually been a lot of thin film work, for instance, on BO2 thin films where they claim there doesn't seem to be enough lattice distortion at all. And that's because I think the techniques they're using are only sensitive to long range distortions, and then these thin films are only short range. So, and you can model this in the reciprocal space if you want, although of course technically speaking that's no longer necessary. But just to show we can. This is left is the data, right is the simulation. Okay. It turns out this is actually kind of geometric frustration that if you have the buckling, for instance, in one plane, the neighboring planes don't know that degenerative is only nearest neighbor plane. They don't know whether to go one way or the other, and so you get very weak correlations. You have to have longer range correlations in the orthogonal direction to generate long range order, as you see in the M1 phase. Okay, so that's a VO2 example, and I think that's that I'm sure that these things would give valuable information on a lot of other such electronic phase transitions. Okay. Hidden order and Canadian linear, this is to introduce the whole machine learning approach. And to explain machine learning quickly, we're actually not talking about convolutional neural networking. We're not creating. This is just unsupervised machine learning, which, as many of you know, is a way of clustering the data according to what seems to be natural clusters, by minimizing the log likelihood function. Okay. The advantage of this is that it's actually the results of this clustering is easily interpretable. But the insight that Una Kim and her colleagues at Premala had was that this is ideal for studying systems where you're measuring the temperature dependence over a large number of temperatures of a set of voxels which you consider to be statistically independent from each other. So supposing we have something which goes through some kind of structural phase transition, could be a CDW or something else. Okay, so at high temperature you see one set of bragg peaks, at low temperature you see extra superlattice peaks appearing. All of the voxels that correspond to these superlattice peaks would all turn on at a certain temperature, at the transition temperature. And that means then that, that if you look at the trajectory of every single voxel, and we're not just taking the superlattice peaks, we're taking everything, okay, and then try and cluster them, well, in a simple two-component cluster, for instance, once you threshold it out, say, all the background, which is not doing anything interesting with temperature, you can end up with essentially two components. We have those peaks which essentially are showing no interesting temperature dependence, and those which are turning on the transition. Furthermore, it can tell you exactly where those voxels are that are turning on. Okay, so without having to do any training about crystallography or something, the unsupervised machine learning has identified that all these superlattice peaks are occurring, for instance, at these half-integral positions, and they're color-coded now. So this becomes like a kind of a map, a Google map or something where, you know, green represents forest reserves and blue represents the factory districts. Well, here we're sort of producing a column map of reciprocal space, telling you where all the interesting temperature dependencies are. And this is both useful as a sort of a tool during the experiment, say, particularly if you can do it in real time, and if we parallelize this, we can do this in something like 15 minutes, even though we're dealing with like hundreds of gigabytes of raw data, certainly about 100 gigabytes of process data. You can do it in about 15 minutes. So at the end of a night's run, you can come back in and say, okay, hey, Siri or Alexa, tell me where the interesting part of the space that I should be looking at, and should I be measuring more temperatures, etc., etc. So it's useful on that, but of course it's also useful in terms of actually just providing information on that temperature dependence without any selection bias, using the entire volume. Now, one of our first examples we tried this on was cadmium rhenate, and our reason for looking at this was because of this. It was one of the candidate compounds for Liang Ku's prediction of parity breaking for the electron phases in systems with strong spin-orbit coupling. So, you know, multiple kinematics and metallic ferroelectrics, things like that. And actually, as pointed out by James and Frederick Schlottman in their review, there are an awful lot of cases, it seems, where the systems with strong spin-orbit coupling seem to go through some phase transition, but we can't tell what it is because the peaks are too weak. Sometimes non-existent. And so you see the word hidden order applied quite a lot to the material. In cadmium rhenate, actually the peaks had been seen, but there was a dispute about what was the primary order parameter. So David Shea had done second generation spectroscopy, and his claim was that actually the primary order parameter was not the EU, which had earlier diffraction results suggested, it was this T2U. There were two transitions actually in this material, that's 200 Kelvin and about 115. So we ran, we did measurements over a lot of temperatures, and here are some of the trajectories thrown out by XTech. I should have said XTech is the name of the program that the Cornell group have written, and they identified 4 clusters. And if I concentrate just on, say, the 2 clusters of peaks which appear at the 200K transition, firstly, of course, you can see exactly where those peaks are in reciprocal space. You can also tell what is their temperature dependence, and in fact, you can even fit critical exponents to these temperature dependencies. But there are some, for instance, which you know, there's a lower first order transition 115 Kelvin. There are some peaks which suddenly plummet, others which suddenly shoot up, and there are other systematics with those peaks which I'll show in a second. But it turns out that knowing where these Q vectors are, we could get an analytic function for the intensities, And so we know how these intensities vary according to the cadmium and rhenium ion distortions. And it turns out that there are actually positive and negative cadmium antiphase cadmium and rhenium distortions in this material, which is causing this divergent temperature dependence in the two. But the critical exponent of both of them, going from the distortion, is 0.25, which is actually interesting because it's a 2D XY or exponent. And that's actually what you would expect for the condensation of a two-component EU mode. Basically, there are two possible ground states. There's I4 bar M2 and there's I4 122, and they form they're nearly degenerate, so you form this kind of maximum gap potential, and so you're going to get very strong fluctuations within that, which will lead to an exponent just like this. But it definitely is the primary exponent. So there is definitely, so we're in disagreement with the SHG results on that. Okay, and then as I say, we can actually even analyze what are the distortions that are given right. Interestingly, we're getting the distortions not from fitting the drag peak intensity, but from the temperature dependence of the intensity, which is very cool. But there's more than that. If you're going to have something with a maximum potential, you can get very strong fluctuations. You're going to get Goldstone modes within that ring, and indeed we see them. Here is the diffuse scattering around the drag peaks, and XTEC can actually foster diffuse scattering as well as the drag peaks. And so, if you do that, we see that the same sets of two peaks that I showed before have distinct diffuse scattering around them, okay, with distinct temperature dependencies, and you can cluster them as well. Now, so if you take the peaks which this yellow peaks are ones which are very sensitive to the z-axis distortion of the cadmium rhenium ions, the green are sensitive to the in-plane. And if you look at the fluctuations, they're reversed. So in other words, you get stronger fluctuations around the ones which have the z-axis fluctuation than the ones which have in-plane fluctuations. And so you can characterize this. The first time I think we developed selection rules for the Goldstone modes from essentially an analysis of hundreds and hundreds of drag peaks. McLeod did a Landau theory analysis, which just for completeness I'll show, which shows that basically you can model this. There's actually critical scattering close to the transition, and then these Goldstone modes, which are very similar to what we produce. And so what we believe is happening is that at the 200 Kelvin transition, it goes into the 5-4 M2 mode, which is C4. But you get very strong fluctuations within the maximum potential, which eventually leads to a first order transition into the 5-4 1D2. Okay. So, by the way, if you have any questions, answer. I realize this is a bit of a rush through.
I have a question.
Oh, yeah, please, sir.
I apologize if this seems very basic, but is there a thing that the machine that was done here that would have been that you couldn't have done yourself, or that how much faster was this? Than you, very smart human.
Well, actually, in cadmium rhenium, I did that. I tried that. I sort of thought, okay, I'm going to take this drag peak. I'm going to manually fit a temperature dependence. So I'm going to take this drag peak. And there are actually subtle variations from one drag peak to the other. And in fact, what happens is, of course, whether it's your sensitive to the z-axis or the in-plane components depend on the angle with respect to the c-axis of the q vector. So you have a whole range of possibilities. And I gave up after a while because it was just impossible to systematize it personally. Now, the clustering, of course, has to be treated with caution because, just with any machine learning technique, it's giving you an answer and you don't necessarily know exactly, well, certainly the in which that answer was arrived at, how it was arrived at. But, and so I'm not saying that, you should naively just take any clustering and say, yeah, this is the truth. But it is incredibly faster than actually trying to look through hundreds of peaks. And of course, you're doing it without selection bias. It's the plague of, I started off as a graduate student on a triple axis spectrometer, which is the ultimate in selection bias. You look at a single Gruen zone, often single wave vector. You do a constant energy scan, and you assume that that is going to give you something that is characteristic of the whole material. Anyway, so So the Bragg phase, this is actually the latest analysis, and again, credit really should go to, well, definitely should go to Una and Krishna, who've been the creative forces behind a lot of this work. So the origin of this story, I don't know if you've not heard of Bragg glasses before, but the origin of this story goes back to the 70s and the result from Humery and Marr that if you have an autoparameter with continuous symmetry, that it's unstable to obviously small disorder. And the idea behind it is that if you have, is that you're going to have a disorder potential, which is trying to pin, say, in this context of a CDW, a disorder potential is trying to pin the CDW to the dopant, say, and you have elastic restoring forces that are trying to homogenize the phase fluctuations. And you can, if you try and optimize for those two competing forces, you end up with density function series with decay exponentials. You basically have short range order below a couple of dimensions. But it was realized in the 90s or so that actually the phase is bounded in these materials. So that there can be solutions to this where you're not, this assumed a linearization of that disorder potential. Explain that. So this is a VAR times phi. If you didn't assume that, then you can have circumstances in which the phase fluctuations decay logarithmically rather than as power law, and the result is density functional that decays 1 over r, and that actually leads then to divergent structural correlations. So these divergences are happening at the CDW wave vector, but it's not a Bragg peak, okay? And it's incredibly difficult to tell the difference between this and a Bragg peak because basically they're both essentially resolution limited peaks, okay? So Bragg peak, the whole idea behind Bragg has been around for 30 years, but there are very few cases where people feel that they've confirmed it's true. And the approach that Una and Krishna came up with was, okay, we wanted to have a high throughput measurement that used the machine learning tools that we developed. And one high throughput method is to use the line widths of the materials. To this is now coming down to the Bragg glass transition. The idea being that phase fluctuations would have a Q independent line width, whereas fluctuations due to lattice displacement will have a Q independent. And so if you can separate out the Q independent part of the line width, then you can determine whether that diverges in a way that's consistent with Bragg glass. So the material we're looking at is one that Ian Fisher and co have looked at for a while, and indeed they proposed that this might be a Bragg glass from an analysis of dislocations within STM data. And so pure erbium telluride, this is in erbium telluride, palladium. Pure erbium telluride, there are two transitions which X-Tech identified here, P65 and 035 or something, I don't know. There are actually, you have these sort of square planar, we have these bar layers of tellurium, but the square planar actually thin. And so you get it's all barometric, you get firstly a CDW along one direction, then a lower temperature, and orthogonal CDW. Okay. And doping with palladium suppresses the CDW order. You only have a really nice order parameter for the pristine compound, and you dope if you get some rather weird looking order parameter functions. So here's the idea, and they're making use of the fact that having done X-Tech, we already know where the peak intensity is. What are the pixels that contribute to the resolution limited peak? So we use those peak intensities. And they came up with this peak spread function, which I must say as an experimentalist I was initially rather skeptical of. It works remarkably well. The idea is you take the total intensity within the peak and you divide by the maximum peak intensity, and that's proportional to the line width. And they did some benchmarking and using more conventional techniques, but showed that this really did work. And so now you can actually analyze the line widths using X-Tech, using supervised machine learning, and identify what is the Q independent term in the widths. And so here you see actually that the line widths diverge as you expect with the pristine compound. But if you look at the other composition, what happens if you go too high, then they saturate because too much intensity leaking out of of these peaks, but in a region above the resolution limit, you get this very clear temperature dependence, which actually it seems to be linear. Instance, we saw that in ivory selenide as well. I never understood it. Here, once you get below a resolution limit, then you won't see a change anymore. But if you extrapolate that down, you can get a very precise measure of where the phase component of the alignment goes to 0, where you expect the bright glass phase to be. And it turns out that if you put that on a phase diagram, it exactly corresponds to the temperatures at which there was a change in the anisotropy of this transport. So it's consistent with previous transport measurements, but provides a new insight into the prevalence of bright glass behavior. So I wanted to show that because it's not just a matter of finding order parameters. Yeah, not half an hour that I talk about 5 minutes. Thank you for questions. Sure. Okay, so I'll finish now. So I wanted to say that it's not just for order parameters, but you can come up with completely new ways of analyzing the data because we have such large data volumes. Okay, so this is my conclusions, which are basically that I think this is an interesting technique that I want to be made aware of, and I'm happy to talk to you about it.
So Bragg glass is a distinct phase of matter, so of course it's extremely exciting to establish it. But now that you've done this machine learning, can you then go back and look at the right peak to see that you have a power law cusp, not a Bragg peak?
Our resolution is not enough to actually sort of be able to fit tails to the power law tails, so that's what you're asking.
You would like something that's sort of unambiguous because you're making a very strong claim.
Yeah, no, I mean, of course,
we made the same claim, so I'm not criticizing you.
No,
I'm nervous.
I agree. We shouldn't say we prove this is break glass. I'm saying this is very strong indication of break glass behavior. But you're right. I mean, in principle, if we were to do ultra high resolution measurements, then it might on a completely different machine where we did essentially home in on 1 or 2 peaks, then it might just be possible to. The other thing we've never done, which I regret, is to look in the PDF space, and that's just because I've got ran out of time to do it. But because there, you might actually see these decaying tails as changes to the long range correlations in real space.
Yeah,
and that would be actually a really good thing. But no, you're correct. Please.
Just a small comment regarding vanadium dioxide. You mentioned something that you want to see first principle calculations. So the word of caution, that vanadium dioxide dimers form through, of course, it's very well known and well established that it's not pulse. What happens is that they form actually a true singlet, which is not a singlet orbital state and cannot be described by density functional theory by definition. So we worked a lot towards describing radiation damage in vanadium dioxide, and it turned out that if you try to put straight DFT or DFT plus U, whatever, it actually freezes in the anti-ferromagnetic state, which is not right. And the only way to handle that is to treat vanadium as 2 different species, those which are paired as in fortic non-magnetic, which is better than nothing, closer to singlet than anything, and those which are isolated end up being strongly correlated individual ions controlled by Hubbard correlations. So with whatever you're planning to do here in DFT, you should be extremely cautious. It's a worst possible scenario, DFT.
No, I won't be doing any DFT, but
I mean, your collaborators, whatever.
Yeah, so you're saying though that even the vanadium ions which are not involved in the dimer, they're strongly correlated.
Well, they are strongly correlated. Those which are involved, they form a singlet. And if you try to put correlations in the mean field way as we do, well, you can do cluster DMFT, which Gabi Kotler did, and that works. But that's prohibitively impossible for this large supercell that you need to emulate there.
Okay. Maybe one last question. Wait.
Have you or the Cornell group thought of, I mean, maybe that's not usable, but thought of using X-Tech to come up with a way of separating the Bragg from the diffuse scattering, other than just punching out some circle close enough to the Bragg peak? Is there something you could do in that direction?
Okay, so we haven't thought about using machine learning for that. The approach we have, yeah, I mean, of course, it's true that it's somewhat arbitrary with punch out.
Right.
We say, here's a very peak, here's not. And sometimes you get like that. Our applied mathematician friends are actually looking to compress sensing as a way of, and the idea behind that is just that you can vary, say, the volume to produce the resulting PDF, which minimizes fluctuations, which are probably going to be some kind of spurious fluctuations. Although that probably will be computationally really, really expensive. So I don't know, but yeah, it may be that AI is. I should talk to them about that. We've got some creative ideas.
Okay, well, let's thank our speaker once again.
No, my first time, but let's put the. Yeah, but then it just stops right. Oh.
Okay, yeah, yes. All right, well. So the last talk of today will be given by one of our own, McLeod from School of Physics and Astronomy, and it will be on, it has the title Under the Nano-Lens, Revealing Quantum Materials Through Near Field Optics.
Thank you, John, and thanks to all the organizers for inviting me all the way from across Muller's Block, since my laboratory is over in the Physics and Nanotechnology building, all of which you can kind of see in this picture. Okay, so you've been here for at least a day, so you know that our campus is sitting right. Take a walk over to the Mississippi River, right there in the coffee breaks. And so I'm from School of Physics and Astronomy. You know, I think it's somehow I think the organizers are mind readers because everything I'm going to tell you about today has gotten some nucleation barrier overcome. We'll talk about VO2, we're going to talk about STO, but I'm talking about a variety of these materials that have already been introduced to my favor, but under the Nano-Lens, that is to say, you know, in the spirit of new techniques, new scattering techniques, new nanoresult techniques, near field optics is now coming into its own as a capable and also quantitative tool for also study of these quantum materials in real space. So in other words, using photons, but now extremely high spatial resolution, circumventing the diffraction barrier. I'm going to tell you a little bit about how that works. But first, so that we're all on the same page, I think we can all acknowledge that quantum materials are natural hosts in homogeneity, which poses our problem. How do we get at the nanoscale physics going on in these systems if we're limited in large part to bulk probes? And in no small part, we can rely on inferences, but I'll, of course, as Yogi Berra once said, you'll be surprised what you see just by looking. And so key to that is finding an optimal technique that can circumvent the diffraction limit and take a look in real space at these quantum materials. So I just want to showcase a couple of examples to get us all on the same page when it comes to quantum materials and their various guises, including insulator metal transitions, such as in VO2, which Raymond introduced in his talk there. How generically these classes of quantum materials showcase their action at very small length scales. These happen to be nano-optical images, some of the first collected on a quantum material, that Drosophila of VO2, showcasing the insulator metal transition as being really this percolated phase transition. One has to really go in and see with 50 nanometer spatial resolution to resolve individual groups and avalanches of unit cells undergoing this first order metal insulator transition together in some cooperative fashion. Going on, you know, through the taxonomy of different quantum materials, many of us are familiar, of course, with the fact that, especially the underdoped side, high temperature superconductors like the cuprates showcase competing phases all the way down to nanoscale. How do we know? How can we see? Thank goodness we have tunneling
microscopy and tunneling spectroscopy, as well as, let's say, X-ray Bragg typography techniques to show us where these phases are actually positioned in real space and in what sense of real space they can be. Now, of course, we have a hard time leveraging scanning tunneling spectroscopy for every material under the sun because many of them are insulators. Going into topological materials, of course, owing to the bulk boundary correspondence, the real action that endows these topological materials with their intriguing and exotic macroscopic properties lies at the edge states. So here's an example using a scanning probe technique not dissimilar from what I'm going to tell you about today to resolve the actual electrical response of these edge states, which endow this particular two-dimensional topological insulator tungsten ditelluride with its topological properties. And in the vein of designer quantum phases, whether engineered by illuminating a material with an intense laser pulse or heterostructuring in some clever way, like in the case of the Moiré van der Waals materials, which I'm going to stay away from for the purpose of this talk, except to highlight how nice it is to have an imaging probe that can show you first of all, how the crystal is configured in real space, but also what the electronic properties are that correlate with that structural configuration. Here's the partnership between transmission electron microscopy and a near-field optical technique. Again, not dissimilar from what I'm going to showcase for you today. So now that we're all reasonably convinced that inhomogeneity is there waiting for us, let me give you a flavor of what the outline for the rest of the talk is going to be. I'm going to give you first an appetizer before telling you how this technique works and how it's leveraged on a variety of these quantum materials. And that appetizer comes in the form of another vanadium oxide, V2O3, just to show you what in real space one of these first order insulator metal transitions looks like and what we can learn about the spatial configuration as we image the phases involved in this phase transition. Now I'm going to move on to the next, let's say, frontier for nano-optics is real spectroscopy. We'll talk more about this in the next slide here, but the idea is, of course, we can image these phases all day long if the laboratory is in a good way, but can we learn something about the properties of these phases through spectroscopy? And we can vary the energy of photons, so why not do spectroscopy at the nanoscale? So I'll showcase a little bit of that in the sister compound here, VO2, where life is easy because you have this high temperature inside metal transition. And then I'm going to push this spectroscopy, this nanospectroscopy, even a little bit further in the context of resolving inhomogeneous strain inside of plastically informed oxides. Okay. Spoiler alert: strontium titanate, which we've heard a lot about already today, is going to be the centerpiece of this part of the discussion here. And I'm going to introduce this concept of hyperspectral nanometers. It means a lot of data. And how do you use this data in order to learn something about let's say in this case, the nanoscale strain environment and the optical properties of these solids, inhomogeneous optical properties. And then I'll conclude by just giving you a flavor of which direction this technique is going. It's been touch and go with nano-optics for, let's say, the past 5 years or so to implement this technique, where it can really make a superb difference, resolve the genuine ground states of these quantum materials, and I say go lower in temperature. Much of what I'm showing you right here today is variable temperature phase transitions, but to resolve ground states, we of course have to go to extremely low temperatures. So this has been a technique development, but those gearheads in the audience might appreciate this section. And I should also point out, insofar as we'll be with each other for the next couple of days, and my laboratory is just across Scholars Walk, as I mentioned, stop by. Feel free to have a conversation, and we'll see what this nano-optics techniques can do for your problems. So first, because not everyone in the audience does optics or is an optical spectroscopist, although some of us are, and we've heard some optics earlier today. Let me just give you a flavor of what optics can do to disentangle the nature of competing phases in many of these strongly interacting quantum materials. The most cartoon phase diagram that you may have seen the entire day, courtesy of my good pal Andrei Pustakov. I mean, if we want to caricature our quantum material, if we crank the strength of interactions, or if we go the other way by putting our material under pressure, increasing bandwidth, let's say, we can tune in generically between a Fermi-liquid state and some state, let's say mod insulator, where the electrons are localized going to their mutual interaction. That interaction may give rise to an ordered phase like magnetism, density wave, superconductivity, etc. If only we cool down enough and improve the strength of interactions. Again, total cartoon picture, but many materials reside, of course, inside of this cartoon. And I'm just going to show you, give you a flavor of what optics is actually measuring. If we go, many of us have a concept of density of states. Okay, so if we're in the Fermi liquid, we have coherent quasi-particles at the Fermi level. There's some indications of interactions. So with our cartoon density of states, is a cartoon point density of states, otherwise known as the optical connectivity. Okay, so if one can do optical spectroscopy over some energy range, in principle, the information about density of states is encoded inside of the spectrum. Okay. And a characteristic in this case is the energy scale for interactions, the Hubbard U, which ought to show as a vestige of the joint density of states in transition between upper and lower Hubbard bands here. So this isn't just cartoon story, taking some older data, traditional optical spectroscopy from my former colleague Maggie Stewart on that same material, B203, shows that a lot of these features show up in real spectroscopy data, notably the energetic feature out here at 1.5 dB. Now, if we cool this particular fellow down, we can navigate ourselves through this phase transition between mod insulator and Fermi liquid. We lose a quasi-particle, and that is showcased in optical spectroscopy as well. Okay, so the coherence of quasi-particles drop. Eventually, of course, we open a gap. If we go into the mod insulating state, it goes sufficiently down. In this case, into the ordered state, it happens to be an anti-ferromagnet, the B203. We have a clean gap. We have a signature in the optical connectivity. We have a gap in the optical connectivity, no more trigger response. So the key point here is that if I have a hard time getting contacts to my material, or if the surface is some sort of complicated business, photons fortunately are bulk sensitive. So I can really see into the interior where it's happening in the material. I have broadband energy sensitivity. I can sense both interband and interband responses, okay? Particularly to pull out the natural energy scales with interactions here. Naturally, I'm highlighting the positives. One of the limitations of optics heretofore is that you're essentially probing Q equals to 0, but I'll comment on that in a couple of slides as well. And of course, as a quantitative measure, we're getting access to the gap contacts, the joint density of states. That's all lovely. So photons are good. We all love photons. Of course, we'll be reminded in a couple of slides that we have to play some tricks in order to reveal the homogeneities of these quantum materials using optics. But before that, I want to give you. I'm going to let you taste your appetizer, okay, which is what nanoimaging shows as we actually go through not a cartoon phase diagram, but a real phase diagram of B203. And these are some of the first, let's say, low temperature nano-optical data imaging a quantum material. In particular, going here from the Fermi liquid state into the anti-ferromagnetic insulator, which has a nail order. I'll also point out about this fun material, which was originally classified as, the canonical mod insulator by virtue of its phase diagram. As often is the case, the material turned out to be a little bit more complicated than just the canonical mod insulator picture. But nevertheless, all of the features in the cartoon phase diagram are emulated here. So for the data that I'm going to show you right now, I have to give credit to sample providers. The king of vanadium oxides, Ivan Schuler, provided the thin films grown on sapphire that we imaged using this nano-optical technique through this phase transition. As usual, you have an insulator metal transition accompanied by orders of magnitude change in resistance. That's all nice and lovely. You can see a hysteresis, it's first order transition. All that is very satisfying. We all wondered, why on earth is it the case that unlike a single crystal, this resistive transition is broad over 20, 30, even 40 degrees Kelvin? What did we do wrong when it came to growing the film? As it turns out, nothing. There's some physics there, which the real space imaging will actually show us. So our mandate, generically, maybe I speak for all of us, okay? Our mandate is to visualize these phase transitions and disentangle these interacting order parameters. We have the mod insulator, we have lattice structure, and I should point out also here, as we go from the high temperature to low temperature phase, there is a change in lattice structure owing to the electrons. And the last bit, of course, magnetism. So a couple of things I'll touch on for this B203 example. So enough with the talk, let's see what the phase transition looks like. So here's the plan of attack. We're going to image a little 20 micron spot while cooling the material through its insulator metal transition. How are we going to do this? We got to send some photons in. We'll detect photons out. I'll tell you how later. And we're just going to change the thermometer here. So I'm going to, before getting into what the colors actually mean quantitatively in the actual experiment, just pretend for a moment it's an apple-optical conductivity. So red is metal, blue is insulator. Take my word for it. You should be right to be suspicious when you see values somewhere in between the two of these. But let's just go ahead and see what happens as we cool this fellow down. So again, we're scanning some sort of probe, optical probe over the surface of this material, 20 by 20 micron square. Same field of view all the time. And as we cool, the first thing that you'll begin to notice is that we nucleate some other phase. It's not metal. It has a lower conductivity. One should rightly ask, what is its conductivity? Clearly, that conductivity gets more blue on the scale as we go lower and lower and deeper in temperature into the, as you can also follow the bouncing ball here on the resistive transition. You can see we're going into the insulating state. And maybe right about here at this inflection point, there should be a percolation event that happens, which is something that resistive measures would see in real space. We can kind of witness that as we break up the metallic phase into these isolated islands. And if we cool sufficiently, and we really do have to cool a great deal, we can at last, let's say, get out of the spinodal region and start to get rid of all the metallic phase. Although there are some little domains that hold on for dear life, clearly. Until finally, push it down a bit lower and we achieve homogeneous insulator. No surprise there, but it's what was in between these two phases that is maybe a little bit surprising. Okay. Now, of course, we can play the movie in reverse. And you'll see it's not exactly the same movie indeed that we're playing in reverse when we heat the fellow up. We nucleate the metallic phase. We have a percolation and growth of the metallic phase. We finally bypass also the inflection point in the resistive transition, as we would expect to do. And towards the end here, you can kind of see, is there an insulating phase here? Yes, and exceptionally weak one. Okay, at least based on our color scale here. Until finally, if we warm sufficiently up, we end up in the full metallic phase. And I'll also point out, maybe you can ask me a little bit later, but there's quite a lot to say about these little fellows that will somewhere halfway between metal and. All right. And some of the first questions that I get about this movie is what the heck is the deal with these stripes and so forth. Presumably, if one did a diffraction probe, you would see some exceptionally low correlation right in the order here. Of course, what we're seeing here in real space. So let me comment a little bit on that because it's a useful reminder, I think, especially for the experimentalists in the audience, that long-range spatial correlations, in some cases exceedingly long-range spatial correlations, are a consequence of some physics that we should always bear in mind when it comes to phase transitions, first order or second order. So this is in the context of, let's say, steels and martensites. The martensitic transition is something that's encountered with alloyed steel, whether under pressure or otherwise. The fact that the domains, whatever they may be, take on a spontaneous texture. And this appetizer is one piece of a whole series of measurements on not totally unrelated compounds using this nano-optical technique going through a first order phase transition of some kind, ranging from manganites to Beckgard salts to ruthenium oxides. And what all of these examples share in common is the emergence of this sort of nanotexture. So it's worthwhile to touch base with some basic physics when it comes to that nanotexture. There is, of course, macrotexture that one can find in nature. These are pictures from a helicopter of sub-Saharan African vegetation with length scales of half a kilometer, basically, as these vegetation patterns. And here you can kind of tell that I'm going smaller length scales. Down at the maybe the mesoscopic scale, where all many of us anyway will be familiar with the fact. Uniaxial ferromagnets have spontaneous long-range order, even though it seems like the material would like to be all spin up or magnetization up or magnetization down, but instead you find a spontaneous combination. Keep going down a little bit in length scale, even biological systems. There's in spinodal decomposition between lipids, there's a spontaneous separation into textured domains, in this case, chiral domains. Just to showcase some examples where the physics is actually common between these examples, or so I might argue. And in the case even of underdosed cuprates, the nematicity that can emerge can perhaps be ascribed to a similar physical mechanism as these others. So what's the connective tissue between, you know, all these seemingly disparate examples? And again, I like this pedagogical slide, if anything, to be just a reminder for us that study phase transitions of what we should expect before getting too surprised about the emergence of textures. So for a little bit of statistical mechanics, what have we got? A free energy, let's say. What does the system like to do? Minimize that free energy. And to put a little bit more Landau theory into this section, okay, let me just describe in terms of some order parameter phi, what the energy looks like. And let me tell you what these different terms are in the energy density. Again, total cartoon, but one can apply to each of these examples in some way. What might this free energy per unit volume be? A double well, if I'm talking about my first order phase transition. But we've got some local surface tension associated with the order parameter. We don't like to form domain walls too. So it is the exchange stiffness, let's say, for a magnet. But let us not forget, generically, we might have a long range interaction between the order parameter of one spot and that in another spot. Generic, might be small, might be big. What examples might it be? Coulomb interaction, if this is a charged order parameter, dipole-dipole interaction, strain interaction. And so it's a bit tough to do my numerics all day long on this ghastly fellow to find out what the ground state of the system is going to be for some fixed. Instead, is I can vary the free energy with respect to some little wave vector component. Some, I should say, Fourier component of my order parameter. So what do? I take derivatives of all of these terms inside of my integral. The important bits being the local penalty for forming domain walls, goes as k squared. And interestingly, I end up with the Fourier transform of my interaction term. And is there a situation where this can be less than zero? The answer is yes. You get a shape instability. And a shape instability is nothing more than a particular k vector at which the system drives itself towards a state of lower free energy. And I have the delight of preaching to the choir here with a couple of quotations. One being this one from Sulin and Edelman from some decades ago. For Coulomb and dipolar cases, in all cases between this surface tension business, this k-dependent piece of my free energy can be scale dependent. More intriguingly, can be negative on sufficiently large distances and in particular directions. Okay? And as a consequence, free energy per unit length with segments of domain boundaries, let's say, can be negative. So the occurrence of a microemulsion phase is universal. Okay. And to put that in another way, thank you, Steve. Okay. The apparent contradiction, this phase transition must be first order and can't be as a result of the existence of it. Okay. So what are we saying in many of these contexts is an intermediate phase, which, if we're generous, we can acknowledge as being a phase unto itself. It's a question to ask, and what regime is that intermediate phase actually stable? But if we take those physics and apply them to B203, we should remember that although we do have a first order transition with this double well potential, and I can sort of crank the temperature and change the size of this double well potential. Oh, I haven't changed the size of the double well. All right, we're going to change this double well potential with temperature. But let me also remind you that the order parameter, which might be non-zero in the mod insulating state, might be zero in my fermi liquid state, is accompanied by a distortion of the lattice. And so what if I have a distortion of the lattice? I better go ahead and add my elastic energy into my free energy expression here. Stress times strain. Okay, fine. And without going into many details, though, we can do some mathematical tricks and turn that or realize that it's effectively a long-range interaction between the order parameter at spot R and that at R prime. And what is the nature of this long-range interaction? This is a long-range green function for strain. Okay, so if I put a point, it's as if I put a point dislocation inside of my B203. How does that strain propagate to a distant spot inside of the same crystal? And the answer is sort of a power law that fits the bill for the microemulsion condition. And so if I do a little simulation that includes this bit of the free energy, go ahead and turn the crank. I see something not dissimilar at all from what's observed in the actual experiments. And here I am going ahead and changing the only thing that I can in the simulation here is the effective temperature and tuning the double well potential in favor of one phase or the other. And so there's a appreciable zone in which the microemulsion network is stable. So here's a cute little movie. Just stitch all the frames together. All right, very good. So I want this slide or slides to just serve as a reminder, okay, that generically, if my order magnetism, this microemulsion is something that you ought to expect. And in sufficiently clean materials, you'll see, although the order may be hundreds of nanometers, the patterns themselves may persist across the entire material. So in our case, long-range interaction, spontaneous strain are what our imaging of these domains is identifying and actually quantifying. And I'll also point out that chemists, I guess, have known about this for quite some time. So if you sprinkle some molecules on the surface of some elastic medium, and those molecules have two different conformations, one of these fellows conforms in one direction, there will be a strain that propagates through the substrate. And other little molecules a distance away will experience that strain. And this has been observed also in experiments. So the physics is quite universal. I think it's important just to remember that there's some real physics inside of these fun images. So now, not to go too far over time here, how do we do this technique, right? We're doing imaging below the diffraction. How on earth does that work? So we should remember that the images that I've shown you are about 10 microns in size, but we're probing these materials with low energy light. And the materials distinguish themselves at low energies. Our Mach gap in our B203 is about an EV or so. So we certainly have to probe at low energy. And we know that the diffraction limit says how we can't focus much below the wavelength of light, as described in his famous resolution formula. So the diameter of focus scales is the wavelength divided by the numerical aperture of our optics. And it seems as though for this light with low momentum compared to omega of a c, we're never going to be able to get a small focus, right? As light microscopists for decades until 2014, when the biologists discovered this stochastic fluorescence imaging technique and versions thereof to sort of bypass the diffraction limit. And on that occasion, I like this quote from Physics Today. Starting from Isaac Newton, used a prism to observe sunlight. Spectroscopic tools with optics have remained unchanged for really since the 18th century. Drum roll until now. So we're of course not doing what the biologists are doing, but instead what we're doing is imaging so-called forbidden light. And if we imagine that this is our optical connectivity and we take a Fourier transform of it into spatial frequencies, okay, we can ask the question, how do those spatial frequencies, this optical response, how does it propagate into free space? And we've got this fellow called the light cone, right? So this is our energy axis, and this is our momenta axes down here. Any light waves that come from the material inside of the light cone here will propagate to our microscope. Any light waves that aren't inside of this light cone are going to decay evanescently with a propagation length that is basically controlled by the spatial frequency itself. So here, your Abbe limited, diffraction limit. And if we do an Abbe limited experiment at 25 electron volts, which is not going to show you the distinction between insulator and metal, but if it were, we obtain a lovely image. Unfortunately, we don't have contrast. There's no difference between the two materials at 22 phases, I should say, at 25 eV. So what if we go down to ultraviolet? Again, conductivity is not dissimilar between the two there, but it would be blurred. And here is where I want to be. Low energy photons result in low energy response to these phases, hopelessly obscure. So of course, we're not playing that game, we're playing a different game. We're bringing the near field probe really close. We're putting our eyeball, or putting, as it were, a nano-lens to collect these evanescent waves. So how does that actually work? So just in a couple of words, we have the atomic force microscope probe, which is a little pointy bit on a cantilever. We illuminate that with incident light, infrared if we like, no problem there. And if we do a little zoom in here, we see that our probe polarizes in response to light. And as well, if we bring that probe close to the surface of the material that we're interested in imaging, let's say, then that material will polarize in response to the dipolar probe that's right above it. And now we have two dipoles. It's the electric field. We're going to have strong electrostatic near fields in these two dipoles. So our real probe is interacting with its own image in the sample. And so here's a more mathematical framing of that statement. The polarization of our probe is going to be proportional to how much we illuminate. also going to carry a response to these electrostatic mirrors. And the strength of this image dipole is somehow going to be related to the optical constants of the material, like maybe the permittivity or the conductivity. Right? This is some reflection coefficient. So what do we do in the experiment? We collect the scattered light. Scattered light is proportional to the state of polarization of the probe. So if we collect that scattered light in the detector, then we scan our probe around the surface. We measure that scattered light as a function of position. We get a map, okay, a map of the optical permittivity, map of the optical conductivity. And I should say, to go in the converse direction, I have this lovely map, but what I want to do is extract quantitatively the optical conductivity and permittivity. Well, that's obviously a little bit more challenging. That's an inverse scattering problem. But I'll let you in a secret, we have fast computers and we solved that problem some years ago. Anyway, spectroscopy. If we go in and illuminate at a variety of different energies, we can record a spectrum. Now, this is not a spectrum or a series of spectra from a quantum material, but these are a series of spectra from this little fellow who happens to be a piece of comet dust, okay, with really tiny phases that you want to see. So chemists and material scientists enjoy doing subdiffractional imaging, but we who study quantum materials do as well. So let me jump quickly, maybe only to one example that I have time for, which is combining imaging and spectroscopy to really do this nanospectroscopy on these quantum materials. Here's the example that I want to show you, or the tool that enables this technique. So nowadays, instead of using small single energy lasers, we have ultra fast lasers with tunable energy, and principle all the way from visible range to the far infrared, and kind of digging into the Terra's gap a little bit there to, in principle, go on resonance with a variety of different phenomena that we wish to investigate. System that we use in my laboratory is energy tunable, especially in the infrared, covering this entire energy range with a great deal of reproducibility. So what can we do? We can, in principle, sweep our energies from low energy to high energy and record, let's say, the light scattered off of a probe and perform nanospectroscopy of these. So just to showcase this cute little example, this is the last image of graphene that I'm going to show you in this talk, I promise. But a simple scotch taped exfoliated piece of multi-layer graphene has a great deal of optical contrast owing to the optical connectivity of different stacking sequences and different layers of graphene inside the same field of view. So then what can we do besides acquiring images like this? We can acquire spectroscopy. So going pixel by pixel, let's say through this range right here, acquiring a spectrum at every single pixel provides a means of extracting the optical content quantitatively. And I'm showing here both the reflection contrast as well as the absorption contrast. And I can tell you how we gain access to those two individual responses of the material, which are key to go back to the complex valued optical constants. So just to round out this example, VO2, our nice Drosophila here, demonstrating this at room temperature. We have our insulator metal transition that we've heard a great deal about already. We can acquire images all day long, but let us instead, okay, image at a variety of different frequencies. So these are point spectra acquired on 3 different regions at a snapshot energy, an insulating VO2 or slightly metallic VO2 and the substrate. And I'll speak in a moment about these optical contrasts right here. So using our pulse laser, we can tune the energy of the laser and map the optical conductivity of this correlated metal. It's poised right in the middle of its insulator metal transition, and see which regions have a strong reflectivity and which regions have a low reflectivity, and even tune so far down that we tune to the optical phonon associated with VO2. And here we can see a contrast in the optical phonon of the VO2, particularly between the metal, which is now dark, and the insulator, which is now bright. The metal screening basically the response of the phonon there. So the last thing I want to tell you about in this example, for rounding out, and letting you go to the poster session, is if we go to select locations here, this came as a bit of a surprise in the context of these first order insulator metal transitions. We talked already about the spontaneous texture, but what about the optical response from the microemulsion ingredients inside of this field of view? So this blue fellow is an insulator, this red fellow is a metal, this purple fellow is somehow poised in between. So what we do is go in and acquire spectra from each one of those pixels individually. And these spectra, although I'm not showing the fits here, have associated with them derivative parameters, scattering rate, carrier density, which we extract directly from these individual spectra. So And now I'm gonna go ahead and jump to the conclusion, or something akin to the conclusion. I got 80 slides, so we overshot the conclusion, so let me go back. Okay, well, that's getting close to the conclusion. So where is this going? I will not talk about this, but I will talk about where this is going, which is lower and lower temperature. To investigate the optical properties of quantum materials in their genuine ground state, which has been a Herculean technical development going on here on campus to bring this nanospectroscopy to the ultimate low temperatures. Okay? And for the gearheads, I would really love to chat with you about the opportunities this opens up, both technically as well as for new experiments. And we'll give credit to all the individuals who acquired the data that I showed you today, including who put the lab together to push this near field technique to the next frontier, particularly Ian Thompson, one of my graduate students, William Cho and Chris Ulate, who put together this low temperature version of this near field microscope. There will be a poster right after here, given by Liam, who's somewhere in the audience here, where you can hear more about applications of this technique to do spectroscopy and homogeneous quantum material. So with that, I will conclude and thank you for your patience. Thanks.
We will be canceling the poster session because of what? Not really, just in case someone. Okay, we have time for.
We'll have one fewer poster.
We have time for a couple of quick questions.
In the V203 nano optics data, do you see across the hysteresis loop, do you see any return point memory?
Oh, that's a good question. What I showed you there was only like 2 thermal cycles. It's known that in VO2 and also in V203 there is a strong ramp reversing, some folks call it. And so the sample provider for the VO2 that I showed you is Emma Shirley at Oregon University. And he and I have a collaboration ongoing to try and see the real space indications or hallmarks of the ramp reversal memory process. And just for those who aren't familiar, ramp reversal memory is if you park the phase transition halfway through the completion of the phase transition, reverse course, okay, and then go back forward again, you'll see a signature in the resistivity that some memory has been encoded. And of course, it's encoded in the configuration of the domains in some way. But seeing that in real space so far remains undemonstrated, but we're trying.
So that, okay, so that doesn't suggest any coupling to any strain from the substrate, for instance, especially in the field.
So those who study, let's say, random field easing models and so forth, are of the opinion that the memory is actually encoded inside of the domain profiles themselves. So that's what we would like to see, rather than it being some extrinsic.
So, sort of a related question. I mean, you did a little calculation for the microemulsions, assuming that what we were seeing were equilibrium structures. But to what extent is this equilibrium structures, and what is this, failure to be in complete equilibrium? Is there?
So there is no temperature, of course, in that calculation. I mean,
Well, there is the parameters that go into the effective Lambda theory are temperature dependent.
Yeah,
that was a thermodynamic calculation, and so. But you mentioned things like spinodal decomposition, which would be dynamical.
That's
process.
right. Yes. So you can look at any one of these microemulsion phasions, which are microemulsion configurations, I should say, which are like infinitely degenerate in some way, right? There are characteristics that are guaranteed. For instance, the mesoscopic correlation length doesn't work, and perhaps even.
So yeah, that's the question. Does that depend, for instance, on how fast you cool or something? You get
the length scale actually. Just harping on this one in particular is related to the ratio between the strength of long range interaction,
right,
and the short range.
Okay, so if that's true, then it should be independent.
That's right. Yes, but if you change small details, including disorder, but also the thickness of the film, the orientation of the film, all these things, it becomes now true.
I think the question's about cooling rate, if I understand it.
Yeah.
Yeah. So for all of the patterns, these experimental data here, all quenched. What would happen if we go very, very slowly into the transition that we haven't seen? Whether it be in any way different. I might expect, this fellow's got a little bit of disorder, but I might expect in a very clean sample, these stripes might, you notice that there's 2 orientation of stripes. And I'll talk your ear off about why there are 2 instead of 1. But I'll do so later. I might expect one of these orientations to win out and be homogeneously oriented across the whole sample. But only in a very clean case and in a very slow entry into the booster, as opposed to a plane.
With that, let us thank Alex once again.
No, I do not. I guess that there should be hopefully some food and beverages along with the posters to keep you all happy in a way. Which was has a longer staff release.